So let's get back into the story. So today we're going to be here, which is two more topics we're going to be opening up. The first one is solution concepts. Yesterday we started by introducing multi-agent systems. We did some motivation, why this is interesting. Then we talked about some RL basics, just to set the scene with the terminology. And then we started to talk about game models. So we introduced models like normal form games, stochastic games, and partially resolvable stochastic games, and some assumptions here. But what we did not do is to talk about how to solve these games. What does it actually mean to solve these games? And that's a really interesting question. That's what we're going to be talking about today. And then after that, we have a break, and then we talk about some very early first steps in multi-agent reinforcement learning in these kinds of games and some challenges that we're going to be facing when we do that. So it's still early days here in terms of the topics. It's still very much about the basics. And then starting tomorrow and after tomorrow, we'll be talking about some more recent deep reinforcement learning based approaches. So today is still all about the basics. Before we do that, I wanted to just announce here as well. I did announce this yesterday. So I have posted a link to the coding exercises. There's a link. I think there was a question about that, so I posted it there. And there's also a channel called Coding Exercises. If you go on the link, it brings you to this GitHub website where we put together a small number of coding exercises for Tuesday, Wednesday, and Thursday. So the first one is for today after the lectures. And this gives you a few basic files of code, and then there's a few exercises you can do. You need to fill in some pieces of logic, basically, to implement some of these algorithms. It tells you how to run some of these experiments. In this case, you're only going to be doing some very basic tabular RL and in basic matrix game like Prisoner's Dilemma, which we introduced yesterday. And then in the subsequent days, we will go into the more recent deep RL-based approaches. So I'm hoping this is useful for you. This is completely optional. You can do this in your own time after the lectures. The idea is that it's a jumping board for you, and then after that you can explore and play more with this code base that comes with the book. If you have questions, first of all, use the channel on Slack. It's supposed to be peer support, so discuss with one another, see if someone knows the solution. But if you discover some actual problems with the code, then you can go up on the GitHub page and create an issue. And then Lucas, who created this for me for the course here, he will be keeping an eye on this and can fix if there's actual problems or bugs with the code. So please do post them here. But if it's more about understanding questions, then first try to do the peer support on Slack. I think that's much more useful, and you will get answers more quickly. So that's about the code. And just as a warm-up, I want to get back to this, which we started yesterday. And I think I want to get some more views on this, just to warm up here. So again, why do you want to learn about multi-agent reinforcement learning? Why do you care about this? And what do you want to do with this? Yesterday, we heard some voices, want to get some more people. Hands up if you have ideas, or if you want to share why you care about MARL. And don't be shy, it's just to make friends, break the ice. If not, I'm going to be picking some people with my volunteering algorithm. Okay, I'm going to pick some people. How about you? Yes. Why do you care about MARL? What do you want to do with it?
Well, I am doing my PhD not exactly about multi-agents. I am working more on what it's called physics-informed machine learning, but I am trying to apply this to a series of problems in the field of astrodynamics. And one of the problems I want to try to tackle is the problem of formation flight. And I want to see if it can be solved using some different approaches related to multi-agents. So I am trying to earn as much as I can
Mm.
about this topic.
Okay, yeah, interesting. You here at the university?
No, I am in the University of Girona.
Oh, okay.
It's a bit more north of here.
Okay, yeah, thank you. Who else wants to share? Okay, I'm gonna pick, how about you? Oh, there's an hands up there.
Yeah, so my work is mostly on human in the loop machine learning. So I feel like multi-agent reinforcement learning is a natural framework to model the human agent and the AI agent and trying to achieve some collaborative goal together.
Okay. Is a useful framework to model humans? Why do you think that?
Um, One perspective I think is that humans could observe states which the AI agent may not observe, and that could maybe help with coming with better policies. So
Okay. Interesting. Okay, one more. Who wants to share? One more hand. I'm gonna pick. How about you with the mustache? Yes.
Actually, my work is not related to MARL, but it's a field that I have very little idea about or know very little about, and something I wanted to learn about because it seems very interesting. And I think there's probably a lot of cross connections that I can exploit or things that I can learn, or in the future, something that I might move towards too. But
What are you a PhD student here?
yeah,
Okay, what do you do?
I work with graph machine learning, graph neural networks.
Oh, okay. Graph neural networks. We've used them actually with reinforcement learning as well in multi-agent settings, so you can actually integrate that nicely.
Yeah, I think I saw some work on that, but not much. But yeah,
Okay,
it's
yeah.
cool.
There was a question yesterday about numbers of agents and how that can change over time and whether it's fixed. I'm not sure where the person is, but here we assume that the agents are fixed. There's a fixed number of agents. But we have done work where we assume that the agents can sort of disappear and then re-enter and changes over time. And in order to handle that, we actually used GNNs, graph neural networks, as a flexible representation that you can grow and shrink depending on the number of agents, and you can learn models really effectively in that way. All right, good. So thank you. So let's get back into the actual slides. Just a reminder, the slides are all available on the book website. Again, as I said yesterday, you don't actually have to take photos or anything. You can find that all online, the PDF. And I think yesterday we discovered 2 or 3 typos, which I've already fixed. So you can download that again. All right, so let's get started. Again, this is the book. For those of you who weren't here yesterday, you can download the book and the code and the slides for free on the website. And let me know if you find any other typos on the slides and we'll fix them right away. Okay, so today is about, we're going to be building on the lecture yesterday where we introduced the game models. But today we'll be talking about solving these games. What are solutions to these games? What does it mean for the agents to act optimally in a game like this? What is a solution to your game? So we first have to introduce some basic concepts, joint policies and expected returns of joint policies. And then we're going to be talking about equilibrium solutions like Nash equilibrium. I mentioned that yesterday already. This is the most commonly used solution concept, but there's many others. We need to know about joint policies and expected returns because all of the solution concepts are expressed in terms of relationships between the agents' expected returns. And then there's additional refinement criteria to narrow down the space of solutions we care about. Otherwise, the solution spaces can be very large. And then at the very end, there's a section about complexity of computing equilibria. If we have time before the mid-break, I'm going to get into this as well, but it's very computer science style, talks about NP completeness and so on. All right, so let's talk about solutions for games. This looks very similar to what I showed you yesterday when we did the basic introduction for single agent reinforcement learning. If you remember, I had a similar figure here where I said that an RL problem is defined as the combination of a sequential decision process and a learning objective. And it's very similar for games. So a multi-agent RL problem is defined as a combination of a game model, such as a normal form game, a stochastic game, or a partially observable stochastic game, these things that we introduced yesterday. And you combine that with a solution concept that you actually want to learn. For example, a Nash equilibrium, Pareto optimality, social welfare, and various other concepts that we'll be talking about today. So the combination of these two things describes a multi-agent reinforcement learning problem. Okay, so there's a few comments here. I said already earlier, what does it mean for agents to act optimally in a multi-agent system? This is defined by the solution concepts. Maximizing returns of one agent is no longer enough to determine a solution. That's exactly what we did in the single agent RL case, right? So the optimal policy was simply the policy that maximized the expected discounted return in all the available states. But here, that's no longer possible because any agent's returns will be dependent on the actions of the other agents. So any agent's returns is a function of the joint policy, which is the combination of all the agent's policies. It's no longer just dependent on one individual policy. So we must consider the joint policy of all agents. Okay, what's going on here? That's weird. Not sure what that is. Maybe a compilation error when I compiled the PDF yesterday. I'll check that out. Yes, I'll check that out later. All right, so first, joint policies. The joint policy is the combination of all agents' policies. That's what I just said, and is defined simply as this. Okay, we're going to be using pi. Previously, pi yesterday was just the single agent's policy, but now we're in the multi-agent case. So now we say pi, if there's not an index, is defined as the tuple of all the agents' policies, 1 to n. Remember, there are n agents, and these are the individual policies of the n different agents. And then we're going to say the probability of a particular joint action, which is again a tuple of actions for the different agents, under a particular joint policy pi, as defined up here, is defined as this product here. Okay, so the probability from this joint action, joint policy, that it would select a particular joint action, given the history of the game that we've played so far, so all the past things that happened in the game, is simply defined as the product for each agent in the set of available agents, 1 to n, the product of the individual agent's policy's probability assigned to the individual agent's action in the joint action. Okay, so pi j is the policy of agent j, and aj is the action of agent j in that particular joint action, and it's just the probability of that single agent that it gives to that particular action. So if you take the product, then that is the probability of the joint policy for a particular joint action. And notice here we're actually making a particular assumption, and it's defined in the note down here. The definition assumes that the policies are probabilistically independent, and that's why we have a clean factorization here. And this is important to point out because there are solution concepts where this is not assumed. There are, for example, solution concepts like a correlated equilibrium, where there's actually a correlation in the choices that they have. For example, I'm only ever going to choose action A if you choose action A, and otherwise I will choose action B if you choose action B. So in that case, that would not be independent like that. But this is the most common assumption, and for simplicity, we make this assumption pretty much all the time. It makes sense because if you have agents that are completely decentralized and executing decentralized, then most likely they will not be correlating. Okay, there's a bit of additional notation that we need to introduce. And this is, I promise, I think this is all we're going to need. And then in terms of notation, it won't get heavier than this. But let's just make sure that we're all on the same page. So first, there's this thing that we call a full history. The full history, which is here denoted as H hat, is simply the sequence of the states, the joint observations, which includes the observation for every individual agent, and the joint actions that were executed in all the past time steps, all the way up to the current state and the current joint observation that the agents get. So we have our states from the beginning up to t-1, the joint observations from t0 to t-1, and then the joint actions up all the way to the current state and joint observation. And we call this the full history because this is, if you look at the game from the top, like you have God's perspective, basically, that's all you get to see. But the individual agents, of course, don't see the full history. The individual agents only get to see their own individual observations. They do not get to see the full state. They may also not get to see the full joint action and so on. So for them, it would just be an observation history with their own observations. And then we call it just the observation history. So when we say full history, which is this H hat, we mean this full thing here, everything there is to know basically that happened in the past. Okay, we need this for some definitions that are coming up later. There's another piece that we're introducing here, which is sigma. If you give it a full history, if you apply the sigma function, then it basically extracts the history of joint observations. It's just a piece of notation. And then lastly, if you remember from the different definition of the partially observable stochastic game, there are the observation probabilities for the individual agents, and that was defined only for the individual agents from 1 to n. And now we're saying we're also going to define this joint observation probability, which is simply a product of the individual agents' observation probabilities. So the only difference being that we're dropping the index I here. Okay, so this notation I think should be clear. Is there any questions about this notation? Oh, looking good. Question? Okay.
Thank you. In your formula, in the first row, there is O with small letter T, and explanation is with small letter. I'm sorry.
All good. Is it clear, the question? Okay, it's clear. Okay, good. There was a question there?
Yes, sorry if it is some basic error, but what's the difference in here between the observation and the state? It's not the observation, it's like the single perspective of the agent, and then I guess it estimates the state based on the observation of the state is introduced from God perspective.
The state is the full, complete description of the state of the world. Not what anyone sees, it's just the complete description of the state of the world. So let's say if this is our world here, the state would describe everyone's names, everyone's locations, everyone's information, whatever. But the observations of individual agents is just what they see from that state. So it will be a subset. I only get to see some of you. I only know some things about you, but not everything. It will be a subset of this. In fact, it might not even be a subset. It might be some other information. For example, the pixels that I get to see, which are synthesized based on the real state of the world, basically, right? So it's you can imagine this is either a subset. For example, I only see some of you, there's occlusion, or it could be completely different information like a sensor stream that is actually based on the real state of the world. Does that make sense? Does it make sense?
Yes, it makes sense, but then the state has to be introduced when, let's say, you are running the simulator and you must know the state. So I guess when you deploy this system, you won't get this variable.
Yeah. So if you have a simulation environment, of course, the simulator needs to know the state because the simulator needs to evolve the state, but the agents do not know the state. Okay. And similarly, in the real world, the real world always has some kind of state, right? But I don't know the state. I only get to see things partially through my sensing feed, basically. So that's the difference. We need the state here because there's certain, definitions and pieces of theory that we want to describe. And that means we need to understand how the process evolves over time. But the individual agents do not know this. The individual agents only observe their individual localized observations, which is basically how they operate. Okay, so moving on. There's two ways now to define expected returns. So we've just defined joint policy and how joint policies assign probabilities to joint actions. And now we need to understand, okay, when we have a joint policy, what is the expected return that the individual agents can expect to get if they run this joint policy? And in the book, there's two ways in which we define this. There's a history-based expected return and a recursive expected return. We're going to discuss briefly both of them. Okay, so first, the history-based expected return. Given a joint policy pi, remember this includes all the policies of the individual agents, we can define the expected return for agent I under pi. So that means that every agent uses their policy in that joint policy as the probability-weighted sum of returns for agent I under all possible full histories. So let's see what this means formally. First, we need to define, let's say there's a set that contains all the full histories where t goes to infinity. It's just a theoretical construct. T goes to infinity here. And then the expected return for agent I under a joint policy pi is given by this sum of products here. So a reminder, we're going to be using uppercase U to describe, to denote the expected return. Yesterday, we used lowercase u to just have one individual sample return. And the uppercase U describes the expectation of the returns. This is for a particular agent I, when every agent uses their policy in this particular joint policy. And so it's defined as summing over all the possible full histories. These are all the possible trajectories that the world could have. And then we, as we sum over them, as we enumerate them basically, we have a sum of this product. First, the probability that this particular joint policy would materialize this particular full history. We can compute this exactly. Times the return, lowercase u, that that agent I would receive under that particular full history. Okay, so it's pretty straightforward. If you go back to the notation that we had earlier here, just a reminder, the full history is a complete trajectory of the world with all the states and observations and joint actions, which also includes from which we can compute the returns as well, because the returns are a deterministic function based on all this information there, using the reward function. And if you go back to this here, in the next slide, I'm going to show you how this is computed exactly, but basically, this was just a reminder of what the full history is. And similarly, this is computed exactly by similarly going through the full history and computing the rewards at every time step for the agent. If we're going into the next set of definitions, there's these two things we need to define. First of all, the probability of a particular full history given a particular joint policy. This is a long product you can spell out here, but it's pretty straightforward. It looks complicated, but it's not complicated at all. Okay, so we're first starting with the initial state. We take the probability of that particular initial state, which is given by the initial state distribution. Then we need to multiply this by the particular the probability that the agents would receive this particular joint observation at the initial time step. And then we go through all the remaining time steps from tau 0 to t minus 1. And we apply basically these probabilities. First, the probability that the joint policy would assign this particular joint action under the history that we've observed so far, times the probability with which the state would go from tau to tau plus 1 under this particular joint action, times the probability that we observe this particular joint observation here under the new state and the previous joint action. So it's really straightforward. It's not complicated at all. We simply go through all the information bits in the full history, and we apply the sequence of probabilities that our model gives us. So in practice, of course, we would never do this. It would be impossible to do this in practice because it's a theoretical construct. We have billions or infinitely many full histories that could materialize. We would not want to or not be able to compute even enumerate the sequences, and yet, not to mention computing the probabilities. This is purely a theoretical construct. And then similarly for the expected return under a full history, this is simply the sum from tau 0 to t minus 1, where we apply the reward function Ri to compute the reward at every time step, and we apply the discount factor here. So that's pretty straightforward, and you already saw that yesterday when we discussed the returns. So once we have that, theoretically, when we compute that, we just multiply this by this, PR with UI, and we do this for all the possible full histories. That is the definition, complete definition of a expected return for an agent I under a joint policy. Okay, it's really kind of intuitive to think about this. The way I like to think about this is that imagine you have a start state, and now you have a tree, and the tree has all the possible branchings and trajectories that the future could be. Okay, you take action A, you go there, you take action B, you go there. And then you take action B, you go there, take action B, you go there. You have a tree with lots and lots of branching. Every one of these branchings produces one of these full histories. That's how I can think about it. Okay, and so all we've done now is we take each one of these possible full histories, and then we basically sum over them by taking the probability that the history would happen in the first place times the return that the agent gets in each individual full history. That's all, basically. That's just a theoretical description of the expected return. There's a different way to define this, which looks a little bit more similar to what we did yesterday when we talked about the Bellman equations, which is a recursive definition. And this is useful because a lot of the algorithms are derived from this kind of idea, as we saw yesterday. But on the other hand, it's not quite so easy to understand as this tree of histories that I just explained. But still, it's important. So we're going to go through this as well. So another way to define the expected return under a particular joint policy pi is by doing this recursive definition that looks like the Bellman recursion. And so it looks like this. V is the expected return, or the value, for a particular agent I under a particular joint policy pi. This is just an argument, which is a full history that you pass on. And we use this because there will be a recursion. And all you do is, at this point, building on that history where we currently are, you sum over all the possible actions you could do. You take the probability of a particular joint action under the given joint policy, and then you recurse into the Q function by basically adding that joint action on top of the history that we've seen so far. Then you go down here. That's where this Q function is defined. Again, you get the full history and the joint action that you've just selected. And from here on, you enumerate all possible successor states. You take the probability of the successor state if we execute the joint action, and then you apply this part, which looks very similar to the Bellman equation that you saw yesterday. You have the reward at that point in time, plus a discounted value of the successor state. And you also need to enumerate over the possible observations that you get subsequently, because that's actually what the agents use when they query their policies. So back here, you recurse back into V. Okay, so that's when you've basically extended the history. So the recursion works like this. From V to Q, Q goes here, and then from Q to V at the end, and V is back here. So basically, that's why it's called a recursive definition, but it's equivalent to the history-based definition. It just means that these trajectories that I just explained to you, rather than enumerating them explicitly one after another, which is what we did previously, now we are constructing them recursively by basically constructing this tree step by step. That's conceptually the difference, but it's the same value. And as I said, this is useful because there will be algorithms which are using this kind of recursion, similarly to what we saw yesterday with dynamic programming and temporal difference learning. Okay. Recursive expected return continued. V, as I explained, is the value or expected return for agent I when all the agents follow their policy and the joint policy. Q, as before, is the expected return for agent I when we first execute a particular joint action and then we follow the joint policy pi thereafter. It's the same as V and Q that we had yesterday. And so lastly, given the definition of V and Q, we define the expected return for agent I by basically starting from the initial state and feeding the initial state and the initial observation into V. So that's basically the root of the tree. And if you now execute this recursion, you could recursively construct this tree step by step, basically, in all the branching. And again, that's like infinite. It's a theoretical construct. Is this clear for people? Do you find that's approximately clear? Question there?
Sorry, I'm a bit confused by the notation because here you use V with S0 and O0, and previously I think you used V with S, O, and A.
Previously, as in
Yeah,
here?
in this slide, we feed the action to the so.
Here, V takes a full history, and that's just any full history you give it, basically. And then here, when you execute Q, you need to add as the next step a joint action that constructs the history. It's basically like one step down into the tree of your trajectories. And then when you get back into V, you need to also add the successor state and the successor observations to have a fully defined full history again. And then you can build again next joint action. If you go here, you need to start this V somewhere. So S0 is the initial state in your game, and O0 is the initial joint observation. That's the root of the tree, basically. That's where everything starts, and you build it down from there, basically.
Okay.
Does that make sense?
Yeah.
Okay. I want to say, if any of you feel maybe there's something that isn't quite clear to you about these definitions, for the purpose of this lecture, actually, it doesn't even matter. All you need to do is just to understand that we need to define expected returns. What is the expected return that agents can expect to see when there's a particular joint policy? And these were just two ways of defining them theoretically. But in order for you to follow the rest of the lecture, you don't actually need to know the details of this particular definition. You can just keep in your mind conceptually, okay, V or Q, whichever we end up using, is just a notation that describes the expected return for a particular agent I for a particular joint policy, okay? If you didn't feel these definitions were completely clear, you can go back to them later. But for the rest of the lecture, you can just keep in mind these are simply refers to the expected return. Okay, so with that in place, we can now go ahead and talk about equilibrium solution concepts. Now we're getting into some interesting questions. Now we're going to try and answer some of these questions. What does it mean for a game to be solved? What is the solution for a game? Or in other words, what does it mean for agents to act optimally in a particular game? Okay, so first, there's another concept that we need because that's used to define a lot of these solution concepts. It's called the best response. And that's very straightforward. A best response policy for a particular agent I simply maximizes its expected return against a particular set of policies for the other agents. And so you often see this notation in game theory, and we also use this when you see this minus I. Minus I simply means everyone except I. Okay. So you remove I, agent I, whatever that agent is, and then you keep everyone else. That's what we mean by minus I, basically. That's the idea. And so it's defined as here. You see, we go through all the agent numbers except I is left out, basically. That's what that means. And so a best response policy is a set of policies against that particular opponent set of policies, which maximizes the return for expected return for agent I. So see here, that's what we now use for the first time, our definition of expected return. This could either be the definition for the history-based expected return or the recursive expected return. It doesn't actually matter which one you plug in here. It also doesn't matter if you didn't fully grasp the details. Simply imagine this is the expected return for agent I, and the best response gives you an optimal policy against these particular opponents. Okay? So in other words, as an example, imagine we are playing a game of rock, paper, scissors, you and I. You know what rock, paper, scissors is. Let's say you use a very specific policy which does particular action probabilities, and my expected return is simply my policy that maximizes my return against your specific way of playing rock, paper, scissors, if you know exactly what your policy is. That's the best response, okay? That's where this name comes from. The best response to your actions. Okay, so we need this concept in most of the solution concepts that we're using because it's a nice compact way to describe solution concepts. So here's the first one. This is the Minimax solution concept. And this was probably where all of game theory started. And this is one of these famous results by John von Neumann and Oskar Morgenstern, who first wrote up this result in some German publications, and then later in 1944, I think they wrote a book in English, which is the first sort of foundational book for game theory that started the whole field, basically. So Minimax is a solution concept, which is defined for only two-agent zero-sum games. Okay, so it's a pretty narrow set of games for which this applies. It's just two agents, and it's only for zero-sum games. But that's where everything started, basically. And so it was very specialized in those days. So it's a solution concept when you only have two agents and when it's a zero-sum game. And remember, a zero-sum game means that one agent's reward is the negative of the other agent's reward. So again, rock, paper, scissors means I win, you lose. You win, I lose. That's what zero-sum means, okay? So the existence, so basically John von Neumann and Morgenstern, they first showed that a solution like this always exists for two-agent zero-sum normal form games. And this was a very interesting, non-trivial result. Previously, it was not clear whether something like this even existed. And Minimax solutions also exist for more complex game models. For example, two-agent zero-sum stochastic games. Remember stochastic games, we introduced them yesterday. That's when you have a sequence of states that can be modified by the actions of the agents. For example, games like chess and Go. Okay, how is it defined? Formally looks like this. In a two-agent zero-sum game, a particular joint policy, which in this case is just two policies for agent I and J, is a Minimax solution if it satisfies this thing here. Okay, so what does it mean? It means equation 1 is the minimum expected return that agent I can guarantee against any opponent. Okay, so if we look at this, we take the maximum for agent I, the policy that maximizes the expected return for agent I, given an opponent policy for J that tries to minimize agent I's expected return. Okay, and equation 2 is basically the inverse. It means that now we're switching the roles here, where first agent J gets to pick a policy that minimizes agent I's return, and then agent I gets to pick a policy that maximizes return against agent J. So we're reversing the orders here. And the Minimax solution means that these two things are equal. Okay, and that's a really interesting idea conceptually if you think about it. It means that in a Minimax solution, every agent plays the best response against the worst case opponent that tries to destroy it, basically. Okay, so every agent in this Minimax solution has a policy where I can guarantee certain minimum expected returns no matter what you do. if you're there to destroy me in a Minimax solution, I can guarantee that whatever you do, I will always, at least on expectation, get this particular expected return. And of course, if you're playing badly, then I can get more. But if you play super hardcore and you're trying to destroy me, I can still theoretically guarantee that you will never be able to push me down below this guarantee. That's a really interesting idea, right? This holds for both players at the same time. And so lastly, this joint policy is a Minimax solution if basically every agent's policy is the best response against the other agent's policy. And they proved this, and then suddenly after this, there was a whole range of work that came out where a lot of interest was generated. There's an interesting property about Minimax solutions is that you can compute them very efficiently, and that's by computing a linear program. So first, before you look at this, who knows what a linear program is? Hands up. Okay, only what's that? Say again? I'm not sure what you mean. Okay, yeah, maybe talk about more later. But a linear program is simply a mathematical optimization task where you have a linear set of constraints, and it turns out that you can actually write down a Minimax a profile as a linear program that you can compute in polynomial time. So there are efficient algorithms that compute linear programs in polynomial time. And that's very good for us. It means we can very quickly compute the solution concept for any given zero-sum two-agent matrix game. All right, but I think I'm gonna not go through the details here because it's not so important for the rest of the lecture. It's just an interesting piece of information that you can actually do this. Okay, now we're gonna move up in the hierarchy of solution concepts. We've seen that we can do this interesting idea of a Minimax solution concept when there's two agents in its zero-sum. But now the question is, can we do something like that for more than two agents and when it's not zero-sum? And turns out, yes, we can. It's called the Nash equilibrium. This was the next super important result that came out in game theory, where a lot of people got excited and it was believed that something like this, it wasn't the people weren't sure whether something like this existed. But then there was John Nash, and he first proved that for any n agent, so more than two agents, general sum matrix game, there always exists a Nash equilibrium. And so what does it mean? A Nash equilibrium basically generalizes this idea of Minimax, where every agent is playing a mutual best response against all the other agents. Okay, so it looks like this. We have a set of policies, a joint policy, and a Nash equilibrium means that for every agent I, it means that there is no other policy pi prime for that particular agent I that it could switch to whilst all the other agents remain fixed in order to increase its expected return. It can never switch its own policy in the joint policy in order to increase its expected return. In other words, its own policy is already a best response against all the other policies in the joint policy. And that holds for every individual agent, okay? So often the way this is summarized in language, it means that no agent can unilaterally on its own deviate from the Nash equilibrium in order to improve its expected return. No agent can move away from that to improve its expected return. It's a really interesting idea. It means that there's a strong fixed point solution that disincentivizes other agents from moving away. That's why we call it an equilibrium. They're sort of concentrating on that point, and there's no incentive to move away. So John Nash first proved this, that any game admits a solution like this. And in fact, this is non-unique. So in many games actually have more than one Nash equilibrium. There could be many different kinds of Nash equilibria, and they all have this property that the policies are mutual best responses. Okay, first before I move on with examples, I want to ask, is this clear, Nash equilibrium? Because this is kind of important. So I think at the very least, you want to make sure you understand the Nash equilibrium. People, do you feel it's clear what that means or any questions? Look okay? All right. So let's look at some examples. Can you identify the Nash equilibria in these matrix games? Let's start with the prisoner's dilemma. I kind of gave you the solution already yesterday, if you remember what I said, but if you don't remember, that's okay. Let's play a little game. So if you look only at the matrix game for the prisoner's dilemma, can you try to identify what the unique Nash equilibrium is? I can already tell you in this matrix game, there's only one unique Nash equilibrium. And it's also deterministic. So it's one of these four joint actions is a Nash equilibrium. Any ideas?
defeat on defeat.
Defect and defect. Yes. Why is it a Nash equilibrium?
Because if the other player wants to change, there is no more advantage for the other.
Yeah. So let's do it together. So correct, defect, defect. Remember, in this prisoner's dilemma, the idea is you can cooperate, which means you stick with the other prisoner, or you tell on the other guy and say it was this guy. So that's defect, defect. Turns out that's a Nash equilibrium because if you look at this, if both players do defect, then both players or agents get 3 years in prison, or -3. So let's say the first player stays fixed. We replace a defect, but the second player, the column player here, could now actually switch from defect to cooperate, and yes. So you see, if you do this, then you end up with a worse reward. So there's no reason for it to switch. And similarly, if agent 2 stays on D, but agent 1 changes, which means move from here to here, then you see that it's actually made its own reward worse as well. So for no agent, there's a reason to move away from that joint reward. Okay, it's a Nash equilibrium. That's what that means. And in this case, it's particularly clean because it's only deterministic. It means it's only this joint action. In general, a Nash equilibrium can also be probabilistic, which means that the policies assign probabilities to actions, and then it gets a bit more tricky. Okay, let's look at the second one, which is the coordination game. Coordination game is a common reward game. That's why there's only this one number in each cell. And it means, for example, if both agents pick agent A, then they both get a reward of 10. What is the Nash equilibrium here? By the way, yeah, so here the Nash equilibrium is at DD. What's the Nash equilibrium for the coordination game? Any ideas?
Both AA and BB.
Okay. What does this mean in terms of the policies? Do you mean that the policies would be deterministic, which means they either have to both pick AA or both pick BB, or do you mean that they could be probabilistic, which means they assign probabilities like 0.5 to this and 0.5 to this? That's the interesting question, right? Let's see what the solution is. Okay, so the solution is there's 2 Nash equilibria, and they are both deterministic. So either every agent always plays A, or either every agent always plays B. And if you do that, then you can see already that there's no point in moving away. My question was, you could also have a policy that assigns probability 0.5 to action A and probability 0.5 to action B, and the same for the other agent. But then it wouldn't be a Nash equilibrium anymore, because you could change the probabilities. Okay, and lastly, for the rock, paper, scissors, this is the example that I keep bringing up. And I think I gave you the solution yesterday already as well, but let's see if you remember. Anyone know what the unique Nash equilibrium is in this game? There's only one Nash equilibrium, but it's actually probabilistic in this case, not deterministic. Any ideas there?
So 1/3 probability to choose between any of.
Yes, exactly. It's the only policy for both agents that cannot be exploited, basically. Okay, so I think it's pretty easy, right? And now imagine we're moving away from these simple matrix games. What does it mean to have a Nash equilibrium in a really complicated, partially observable stochastic game? Nash equilibria exist there as well, but things get much, much more complicated because now we have big games or big worlds with lots of states and lots of observations, and still policies can be best responses with respect to one another. But it's not possible to write it down like this. It's hard to see when you look at what the agents are doing in a game like StarCraft 2, for example. All right, so there's an interesting result, which is a fork theorem. I'm not exactly sure why it's called that. I think one explanation that I heard is it's called a fork theorem because it was known commonly by the people for a long time until someone actually came around and proved it formally. That's why it's called a fork theorem. That's the best explanation that I heard. But basically what it says is there are a number of these fork theorems which say that for repeated normal form games, there's actually a set of feasible and enforceable expected returns that can be achieved by equilibrium solutions. So basically it means that there are games, if they're infinitely repeated, or if there's a termination probability, then there could be infinitely many Nash equilibria which are defined over a sequence of actions. I think this I'm going to skip over as well because it's not really important to understand the rest of the lecture, but it's explained in the book if you're interested in that. So more interestingly, let's climb further in this ladder of solution concepts. We've talked about Minimax for 2-agent zero-sum games. We've talked about Nash equilibrium, which is for n agent, more than 2, and for general sum, doesn't have to be zero-sum. And now there's another sort of relaxation, which is called the Epsilon-Nash equilibrium. And this is important because there are certain sort of restrictions in a Nash equilibrium. For example, one issue is that for a really strict Nash equilibrium, with more than 2 players, there can be a Nash equilibrium where the action probabilities are actually irrational numbers. And as you know, irrational numbers are a problem for computers where we cannot represent irrational numbers with infinite precision. And it's also could be an issue for certain theoretical results. So in Nash equilibria, they're also often computationally too expensive. Not only could there be an issue that there is irrational numbers, but also it's been shown that they are a member of a computational complexity class called PPAT. They're actually PPAT complete, and there are no known polynomial time algorithms that compute these kinds of solutions. And that's only for those of you who are for computer science interested. So that's why we're interested in this relaxation, which is an Epsilon-Nash equilibrium. And it basically means we can relax the conditions by requiring that no agent can improve its expected return by more than some amount epsilon. Okay, so in the previous definition of Nash equilibrium, epsilon was 0. There was absolutely no gain you could get by switching your policy, nothing, 0. And you can relax that a little bit. You can say, okay, let's say an Epsilon-Nash equilibrium means that okay, other agents, they can change their policy a little bit, but they will never be able to get more than just epsilon more expected return individually when all the other agents stay fixed. Okay, that's kind of what it means. It's a slight relaxation. So formally, it looks like this. A joint policy pi is an Epsilon-Nash equilibrium for a given positive value of epsilon. If no agent can deviate from its policy by picking another policy pi prime and get more than at most this epsilon value compared to what it previously got. Okay, so this is important because there's these complexity results that use Epsilon-Nash equilibrium, and also because technically in computers we often are not actually able to fully represent strict Nash equilibrium because of the irrational numbers. Okay, so let's look at an example. This is a game that I basically made up just to show an example of how a Nash equilibrium can be different from an Epsilon-Nash equilibrium. In this particular game, there's a unique Nash equilibrium, which is for both agents to play, for agent 1 to play always A, and for agent 2 to always play action C. So A and C. You can see already if you inspect the rows and columns, there's no point in moving away. You would always reduce your reward. But now let's say there's also an Epsilon-Nash equilibrium when we look at an epsilon value of 1. In fact, there's two deterministic ones. One is when we play B and D, and one is when we play A and C. You can see that you can actually change your policy. For example, here I can go from if you pick the BD one, I can switch from B to A. You can see I can get no more than one difference here. But and the same if we switch from D to C for the role player, no more than one. That's why it's for epsilon 1. But you can see with this example that an Epsilon-Nash equilibrium kind of has a problem, which is it's not really an approximation of a Nash equilibrium. It's just a relaxation. But you can see that any one of these Epsilon-Nash equilibria, for example, these two ones that we see here, they can be arbitrarily far from the actual real Nash equilibrium. For example, I could increase this to 1000. I can say that both agents get 1000, and still it's the same two Epsilon-Nash equilibria here. So an Epsilon-Nash equilibrium is not really an approximation of a real strict Nash equilibrium. It can be infinitely far away really from it. And you need to be aware of these conceptual differences, right? So you should not think of an Epsilon-Nash equilibrium as an actual approximation that is similar or close. Because of this example, you can see that it can be arbitrarily far from the real Nash equilibrium. Okay, let's climb even further. We talked about an Epsilon-Nash equilibrium as this relaxation of a Nash equilibrium. Now there's correlated equilibria as well. And you see how the story goes on, right? So you can define these different kinds of solution concepts, and they mean certain things. They mean certain things in terms of how the expected returns relate to one another. That's how they're all described. We can continue this discussion. Now we're looking at correlated equilibrium. This was first introduced by Robert Aumann, Israeli economist researcher in 1972, I think. And he also got the, I think, a Nobel Prize in economics. Basically, the difference now is that for a Nash equilibrium, we assumed that the policies in your joint policy tuple were probabilistically independent. Remember this definition I gave you in the beginning, where it's just a pure factorization of the individual action probabilities. But it turns out that if you do this, it's actually limiting the potential expected returns that your agents can materialize. So he then introduced this idea of a correlated equilibrium, which means there's now a correlation device that all the agents can correlate against in order to achieve better expected returns. I'll show you an example in just a second. So, but basically it's defined like this. Let's say there's a central policy pi c, which assigns probabilities over joint actions. Okay, let's just say for this definition, there's this central policy pi c, and when you sample a joint action, every agent has an action in this joint action, and let's say that's the recommendation that is given to the individual agents, right? So pi c samples a joint action, which is back there, which has individual actions for the different agents, and then they're given to the agents, and they're like their recommendations. The policy saying, I think you should do this, I think you should do that, basically. So agents can then follow this recommended action that they were given by the centralized policy, or they can deviate by choosing another action. Okay, so let's say there's an action modifier. If you give me action A, I take action B, for example, if I want to change certain things. And we say that this centralized policy pi c is a correlated equilibrium if for all agents it's the case that they, on expectation, cannot deviate or have no incentive to deviate from their recommended actions from the centralized policy. So it means that for all of the possible action modifiers, they will not be able to improve their expected return on average. This maybe looks a little bit complicated. Let's look at an example here. Again, there's a game that we put in here just as an example. In this particular case, let's look at first the Nash equilibria, which are not correlated. So they're the standard Nash equilibrium. There are actually deterministic and probabilistic ones. First, let's look at the deterministic ones. One is where agent I always plays action S, and agent J always plays action S as well. Always plays action L, so it gives probability 0 to action S. So we have SL. Then we see that the agents get the rewards of 7-2. And you can see that you cannot deviate from that. Similarly, there's another deterministic Nash equilibrium, which is when agent I plays L always, and agent J plays S always. Again, you cannot deviate from that. Okay, so in these two deterministic Nash equilibria, they either get 7-2 or 2-7 as an expected return. There's also a probabilistic Nash equilibrium, which means that agent I gives probability 1/3 to action S, and agent J gives probability 1/3 to action S as well, and then they get approximately expected return of 4.66, both of them. Okay, so maybe this is a little bit more fair, you could say, because they're the same. But it turns out that if there's a correlated equilibrium, which achieves higher expected returns for both agents. So now let's say we have the centralized policy pi c, and let's say it gives these kinds of action probabilities. To the joint action LL, SL, and LS, it gives probability 1/3 to each one of these combinations of actions. And then for the remaining combination SS, it gives probability 0, okay? These are all the 4 possible joint actions you can do, and it gives 1/3 to these 3 joint actions and 0 to this particular joint action. But then if you do the expected return under this joint policy, you can calculate this, it's straightforward. Both of the agents get an expected return of 5. And if you look before, previously this was either 4.66 or 7.2 and 2.7. But if you look at this one here, 5 is better. And this is simply because we can actually correlate how they choose actions together. So assuming knowledge of this particular joint policy pi c, if agent I receives a recommendation L, and then they know that the agent A will choose either S or L with probability 5, because that's defined by this particular joint policy. And so, if you get a recommendation L, you know that you expect return for in this case is 4. And there's no other action you can do in response to this recommended action to actually increase your expected reward. For example, if you switch from L to S, then you will get a lower one, which is 3.5. So that's interesting. It means that there are games where assuming independent factorized policies actually limits the achievable expected returns that the agents can achieve. And in those games, there could be a correlated equilibrium where there's a joint policy that correlates their actions, and then you can actually achieve higher expected returns. So that's why that's an interesting solution concept. And it goes further. Now there's coarse correlated equilibrium. This is the same as a correlated equilibrium, but now this even holds when the actions are constant and not defined over a particular action modifier like here. So I'm going to skip over this part here. The next thing to say is, as we saw with Minimax profiles, you can actually solve in a correlated equilibrium as a linear program in polynomial time. And that's, again, useful for computational aspects. In Nash equilibrium, on the other hand, you cannot compute in polynomial time because of the nonlinearities in the Nash equilibrium, the factorization, basically. And that means for Nash equilibrium, it's not as easy as writing down a linear program. You actually have to do something else, and it turns out that it's exponential time compute. So this is important now. I have introduced to you a sequence of solution concepts, okay? Minimax, Nash equilibrium, Epsilon-Nash equilibrium, correlated equilibrium, and so on. And there's quite a few things. This is a whole story, basically, where people come up with these equilibrium solution concepts, and they say, okay, this is what I think, what it means to solve this game. This is what it means for the agents to play optimal actions, okay? Different ideas, basically. But what's important to realize is that they all have certain limitations conceptually. And this is maybe the most important thing I want for you to take away from this lecture, because I often realize that in machine learning and in multi-agent reinforcement learning in particular, people are not aware of these kinds of conceptual limitations. It's important that you're aware of them. There's often this idea, okay, Nash equilibrium, that's all we do. We don't care about anything else. But then what are some drawbacks conceptually? I think we need to be aware of this. Okay, so let's do what I think are the most important ones. First of all, a Nash equilibrium is not synonymous with maximizing expected returns for everyone. A Nash equilibrium only means that every agent's policy is the best response against the other agent's policies. But there are many possible Nash equilibria, as you saw, and they may materialize different expected returns for the agents. So a Nash equilibrium can actually be highly suboptimal. Okay, Nash equilibria do not always maximize expected returns. For example, in the prisoner's dilemma, we saw that the Nash equilibrium is DD, but actually you could both play corporate, and that would give you higher expected rewards or expected returns. But it's not a Nash equilibrium because people could actually then deviate and screw you up, basically. Okay, that's why it's not a Nash equilibrium. But actually, it's probably more interesting to do corporate because everyone gets a higher reward, right? So a Nash equilibrium, this is the first thing to take away. It's not at all the same as everyone is sort of doing the best they can do. They're only doing the best they can do with respect to the other agents' policies. Okay, is that clear? Do you feel that's clear what I'm trying to say here? Okay, all right. The next limitation is non-uniqueness. So we've seen some examples which were really clean. There's only one unique Nash equilibrium, and it's deterministic, and you can point with your finger at it, and it's very straightforward. But actually, in many cases, there may be more than one Nash equilibrium. There may be multiple Nash equilibria. And in fact, there may even be infinitely many different equilibria. For example, I mentioned the Fork theorem earlier, which says that there can be infinitely many. And the issue is, it brings us back to the suboptimality. These different Nash equilibria can have different expected returns. So that's important to realize. And the third one I want to mention is incompleteness. So what I mean by that is, a Nash equilibrium does not actually specify what you should be doing if you're in an off-equilibrium path. Okay, so there's this idea that, you know, there are certain full histories which have probability of 0 that would not be ordinarily occurring under this particular equilibrium solution concept. But let's say there's a disturbance now. Let's say we sort of moved out of our path. We're not on this original path anymore. There's something happened, whatever. The Nash equilibrium does not actually tell you how to get back into an equilibrium path. Then you kind of lost, basically, okay? If you're pushed away from the equilibrium path, then you lost. It's incomplete in that sense. And I think that's important for practical reasons, because in reality, there will be certain external factors that you might not be able to control. And so your equilibrium might not be able to execute very neatly. And then it's, you know, it doesn't really tell you how to move back into place, basically, when there's a disturbance. So suboptimality non-uniqueness, and incompleteness, in my view, are some conceptual limitations that we need to be aware of when we talk about equilibrium solution concepts like a Nash equilibrium. Does that make sense? Now is a good time to discuss, I think, if you feel you have questions or something didn't make sense here. Question there?
So just interested. So here, if we want to optimize, so should we optimize for rather the expected return and not the Nash equilibrium? Or because what do we want to achieve when there is a coordinated game, for example?
What we want to achieve is any one of these solution concepts. You have to pick one. You could say, okay, here's my game. Remember the first slide I showed you, the multi-agent MARL problem is a combination of first you pick your game, and then you pick the solution concept that you care about, Nash equilibrium or something else. That is what defines your solution. That is what you want when you want to have an optimal joint policy in that particular game. So when you ask a question like, should they just maximize their expected return? This question does not exist, basically, because they cannot maximize the expected return in isolation from the other guys. What the other guys are doing is very important to what I'm getting, because what I'm getting depends on what they're doing, right? Their actions influence my rewards. So, and that's why we have these different solution concepts. That's why it's not so clear anymore. There's different concepts that you might be caring about. There's going to be more as well after this that I will be introducing, like social welfare and fairness and Pareto optimality. But do you understand what I'm saying when I say that there is no such question like just maximizing your own expected return? It's all about the social dynamics now, basically. Okay, but everyone else, clear or questions about these limitations? Question there?
And not one of these concepts would yield the both cooperate in the dilemma, the prisoner's dilemma game?
No. Yeah.
Okay, so in real life, maybe they would like to get to that solution.
Yeah. Yes. Yeah, exactly. So there are solution concepts like social welfare that I'll introduce in just a second, and they give you different results. Yeah, for that reason.
Okay.
Yeah, exactly. Because of that reason, there's a lot of literature in economics and in game theory where people look at other solution concepts like welfare and fairness, different kinds of definitions of fairness, or there's different versions of Nash equilibria which are infused with an idea of fairness as well. Okay, so let's move on to these refinement concepts. And I think that's the last of this part of the lecture before we do the mid-break. So we looked at various solution concepts. Now let's see how we can add some additional constraints or requirements to make it a bit more narrow, to really say a little bit more specifically what we actually want. For example, by adding constraints about what we find is desirable. One idea is this Pareto optimality. It's named after an Italian economist from some time ago who studied this extensively. But basically, to address some of these limitations that we just mentioned, we can add additional requirements such as Pareto optimality. A joint policy pi is Pareto optimal if it is not Pareto dominated by any other joint policy. So it looks like this technically. A joint policy is Pareto dominated if there's another joint policy where at least one agent is strictly better off than in the previous joint policy. Okay, so we're comparing two joint policies, pi and pi prime, and now let's say there's another policy, pi prime, where at least one agent I, there exists an agent I that is strictly better off in terms of expected return than in the previous joint policy. All the other guys are at least as well off. And if such a joint policy pi prime exists, then we say that pi is Pareto dominated. And we say that the policy is Pareto optimal if there's no other policy pi prime that is actually dominating it. Okay, so intuitively it means that we have a joint policy that gives everyone a certain expected return, and there's no other joint policy, there's no way of changing this, where at least one agent is better off without making anyone else worse off. That's what it means to be Pareto optimal. And this concept is actually used a lot in all kinds of optimization in economics. So it's not just here, it's useful for a lot of research. Okay, let's look at an example. This is a game called the chicken game. We just saw this game earlier. There's these two actions, S and L. By the way, just to explain the context, It's called chicken because I think the idea is you have basically two cars that are sort of racing against one another, and one, the question is who's wearing off first? Who's the chicken? Who's chickening out first, basically, right? And of course, if both of them keep going straight, then they will collide, and they're both dead, I guess, and then they get no reward. But one could leave, basically, and then the other one gets a big reward because it's the big hero, and the one who's left is the loser, but at least is still alive, basically. Like, that's the idea. And if they both leave, then they don't get the full reward because I guess there was not a single winner. But that's basically this idea of the chicken game. What we're showing here is the interesting thing on the left here. So here, what this shows is for agent 1 on the y-axis and agent 2 on the x-axis. These are the expected rewards they can achieve for all the different possible joint policies. So every blue dot here shows basically if the agents choose a particular joint policy that represents that dot, then they get this kind of combination of returns. So, for example, 1 and 0 point, what is it, 2 or something. Each one of these dots corresponds to the expected return that the two agents get under a particular joint policy that exists in this game. And the Pareto optimal joint policies are the ones that are shown in red here. This is also called the Pareto frontier, as you can see here, because it's at the frontier. Then there's also other markers. For example, we have a marker for the two only deterministic Nash equilibria, which are at the corner points here, and the single probabilistic Nash equilibrium that you saw earlier, which is here in the centroid. And you can see, this is interesting. Pareto optimality, if we consider this now, there are actually joint policies where both of the agents are better off, but there might not be a Nash equilibrium in the strict sense like shown here. Make sense? I think it should make sense, right? It's sort of a nice graphical depiction. Okay, so let's move on, and there's a few more concepts before I wrap. So there's now also this idea of welfare and fairness, and there's really easy definitions. These are the most basic definitions that I think we can come up with. There's more complicated definitions for welfare and fairness. Okay, so let's first say welfare. Welfare is simply the sum of the expected returns of the individual agents under a particular joint policy. So when we want to say that we want to have a welfare optimal policy, it means that any joint policy that maximizes the sum of the expected returns, okay? Now we care about the sum of everyone's returns. If we take them together, we have the total return. That's the thing that we want the joint policy to maximize. There's this idea of fairness, which is similar, but not the same. Fairness is now not the sum, but the product. The product of these expected returns is what we want to maximize. Similarly, we say joint policy is fairness optimal if it is maximizing this kind of product. So, you can see how the story changes now, right? You see how we can change our definition of what it means for agents to play optimally. On the one hand, we can say we want them to play like a Nash equilibrium. And that only means that everyone is playing a best response against the other guys. Or we can say, I don't care about Nash equilibrium. I care about maximizing welfare. And then it looks different. It looks like this. We want to have a policy that maximizes, for example, the sum of the expected returns. But anything that does this here might not be a Nash equilibrium, right? For example, this could correspond to cooperate, okay, which is when they both get a higher welfare, when the sum of the returns is higher. But every agent could deviate to screw the other agent, basically. And so it's not a Nash equilibrium. So you have to decide for yourself, for your application in your game, what do you care about? What do you want the agents to learn? Here's another example. This is another common game called a Battle of the Sexes, which is, I don't quite remember the story. I think it's about going to the same concert or something like that. It doesn't actually matter. It's just a reward description here. It actually says here, two agents are agreeing to meet either at location A or B. Each agent has a particular preference for one or the other location. Yeah, so that's where these rewards are coming from. There's two deterministic Nash equilibria, which is AA or BB. And they're also fairness optimal in this case. So we have a similar plot here that you can see, where all the blue dots correspond to a combination of rewards the agents can get on expectation for a particular joint policy. And you can see the topology is now non-convex. This is a different kind of topology. The deterministic Nash equilibria are the triangles here. The probabilistic Nash equilibrium is the X here. And you can see that there's only two Pareto optimal solutions, which are the red dots here. and they are coinciding with the actual two deterministic Nash equilibria here. So we know that they are Pareto optimal, which means and also they are fairness optimal. That's what I wanted to point out, which is the circles here. So at the same time, they're fairness optimal, which means that they happen to maximize the product of the expected returns. And it turns out that in this case, it's actually the same as also being in a mutual best response with one another. This you can create a script to plot something like this very easily yourself, and then you can play around with this. You can create your own matrix games like this here, and you can run your own script and produce this kind of plot, and you can see lots of interesting topologies in terms of the expected returns. Okay, the last solution concept, I think, then we're done with this part of the lecture, is very important. This is called regret. Okay, so regret measures the difference between the rewards an agent received versus the rewards that it could have received if it had picked different actions in past episodes. That's where this idea, this word regret comes from. Oh, I'm regretting that I didn't pick A instead of B. That's where this word regret comes from. And this is used very extensively in all kinds of theory in learning in games where they have shown interesting relationships between minimizing regret and combinations or relationships with equilibrium solution concepts. Just to wrap this up, let's see what this means formally. In a non-repeated normal form game, assuming that the other agent's actions remain fixed, the regret is defined as shown here. So is the maximum action A, where if you go through all the episodes that we played in the past, if we swap the action that we actually played with the action AI that we're picking here, our action here, then basically it's the difference in the rewards that we got there. Okay, so if we play a game of rock, paper, scissors 10 times, and you play your actions or I play my actions, and I keep your actions fixed, you're not allowed to change, then my regret is whatever single action, if I replay that single action against the actual actions that you played in the past, is the difference in the return, basically, between the return that I actually got and the return that I could have gotten. But you can already see there's a problem with this definition, right? Which is that in reality, your actions, of course, would have been affected if I had changed my actions in the past, right? There's nothing to say that you couldn't have changed your actions as well. But that's just a part of the conceptual definition here. Okay, let's look at a particular example here. Let's say this is a game of Prisoner's Dilemma. You remember this game with corporate and effect. Let's say we're playing 10 episodes. Okay, we're repeating this game 10 times. There's the rows here which correspond to the actions that we actually played for Agent 1 and Agent 2. Okay, Agent 1 played C, C, D, C, and so on. Agent 2 played C, D, C, D, and so on. And then in the row underneath, you get the reward for Agent 1. Right, so if we both play corporate, then Agent 1 gets a reward of -1. And so you can see that if I compare this now with the actual reward that if I had fixed a particular action instead, for corporate, this would have played, in fact, then I get the same, of course. But if I had played D instead, then I would have gotten 0. And basically, you can fill in these rows and then sum them up, basically. And you can see at the end, Agent 1 receives a total reward of -21. But always playing D would have resulted in a total reward of -15 if I keep the actions of the other agent fixed. So the regret because of this is 6. Okay, that's what the regret is. I could have picked something else. I could have gotten 6. A higher expected a higher return. So my regret is 6. And it turns out that you can define algorithms. By the way, you can define the same thing also for stochastic games and partially observable stochastic games, but let's stick here for now. It turns out there is algorithms that you can design that are driving this down to 0. They are choosing actions over time so that on expectation, the regret and the limit will be 0. That's basically what they're designed to do. And there's interesting theory that shows that when you have this kind of situation where in the limit the regret is 0, you push down the regret, there's relationships with Nash equilibrium. I'm going to skip over this part. There's this last part here before we wrap up, and then I think it would be good to do a break. I want to see if this is actually relevant to people here. So first of all, can I ask, who here has a computer science training and knows about complexity classes like NP completeness? Hands up. Okay, around about a little bit less than half, I think. I'm not sure how relevant this is for everyone in the room here, but I think I do want to say that there's a whole area of research which is algorithmic game theory, basically, where people are studying the computational complexity of computing these kinds of solution concepts, like a Nash equilibrium or like these other ones that you saw. How hard is it from a computer science perspective to compute these solution concepts? It's an important question, right, for computer scientists. And it turns out, I think I'm going to just say as much as that computing a Nash equilibrium is a type of total search problem, which is a complexity class, and it's in particular a type of p-pad completeness class. And for this kind of for these kinds of problems, there are no known polynomial time algorithms that can compute these solutions. So what it means is that computing a Nash equilibrium, or in fact an Epsilon-Nash equilibrium, which is the relaxation, which includes a strict Nash equilibrium, is not possible in polynomial time, not that we know of anyway. And the takeaway for you is that multi-agent reinforcement learning, even though it's cool and we care about this and it does a lot of really interesting things, theoretically speaking, it is bounded by the same complexity. So in general, a multi-agent reinforcement learning algorithm will also be exponential time. It's not a silver bullet, okay? Even though you can do things like StarCraft and other things, theoretically speaking, it's not actually something that would solve these games in general in polynomial time. What we can do, though, is to identify certain structures in games, certain assumptions that the games might uphold. And then we can exploit those structures to learn more efficiently and have more efficient learning algorithms. And that's what a lot of research is doing. So basically, that's a summary of what I would have said here. Would have, talked about the complexity, would have mentioned end of line as an example of which is a complete problem for the p-pad complexity class, describe it in more detail. But the most important thing for you to take away is this part here. Implication for MARL is that algorithms are unlikely to be a silver bullet because finding a silver bullet for finding a Nash equilibrium efficiently. I think I'll leave it at that because it could be quite dry otherwise. So this wraps up the first part of today's lectures. Just in summary, we introduced this idea of expected returns for joint policies, which we then use to define a series of solution concepts. For example, Minimax for two-agent zero-sum, Nash equilibrium for n-agent general sum, and various relaxations, for example, introducing correlation and having refinements like Pareto optimality and also welfare optimality and so on. So we talked about these different solution concepts. And remember at the beginning, we said a MARL problem is defined as a particular game plus a particular solution concept that you care about. This is the game that you operate in, that you learn in. And this is what you want the agents actually to learn, this particular solution concept, like a Nash equilibrium. So everything we talked about was basically in that spirit. And now in the next part of the lecture after the break, we're going to be talking about the very first steps in multi-agent reinforcement learning in games. Some very, very basic ideas without any deep learning. We're only going to be talking about some very basic ideas of applying reinforcement learning in games to learn some of these things. And I think with that, shall we maybe continue maybe at 11:40? 11:40, okay? Okay, so see you back at 11:40, and I think we have a coffee break then. Okay. We're back. So I think you mentioned there's some questions online we may want to go through first. Just one question? Okay, let's do it.
Alejandro is asking, would a set of reward maximizer agents, for example, Q learners, converge to a solution minimizing regret?
So say again, question?
Would a set of reward maximizer agents, for example, Q learners, converge to a solution minimizing regret?
Commercial solution minimizing regret. Okay, interesting question. I mean, Q learning is not designed to do anything with regret. And I'm not aware of any work that tries to create this kind of relationship. Q learning is not even known to converge to Nash equilibrium in the general case. It's been analyzed under certain very strict conditions where we describe in the book also where it's able to achieve equilibrium, but it's under only very limited situations. So this question already for Nash equilibrium, I think Q-learning would not be in a position to give you a Nash equilibrium in general. Yeah, so I think the answer is negative, pretty much. Okay, so but actually we're gonna get into this a question there.
Does the regret have something to do with explainability in the context of these algorithms? For example, I don't know, something like shapely values or something like that.
With explainability, that's
Yeah.
interesting. What do you mean?
Because the reason why an action was taken over another one can be understood as.
Okay, yeah, that's an interesting question. I've not thought about it this way. I don't know. I don't know, to be honest. I think so. In my group, we do a lot of work on explainable AI and interpretable AI, but we've never looked at it from the lens of regret. I know that shapely values have been used to do analysis of the impact of various features and inputs in neural networks, right? So maybe you know this kind of literature.
I don't know much, but I know that they are considered like players in a game.
Yeah.
So
yeah, I think my answer is I don't know, but it's an interesting question. Yeah.
But then, like, if your objective is to minimize regrets, then this is not valid anymore because you will not be able to explain why.
I mean, to be honest, regret has its own limitations. For example, the thing I mentioned where we're just assuming that the other agents are not changing their actions. In reality, if I change my past actions, you would change your actions too, probably, right? But regret assumes that that's not the case. And, when we learn, though, then for sure it's the case, you would also have changed your actions. So in that sense, I think regret has its own kind of set of conceptual limitations. And because of that alone, I think it's probably not a very good concept for explaining anything, to be honest. It's just a simple mathematical concept. And it turns out that even with these weird assumptions in place, like that you don't change your actions, if we have an algorithm that minimizes regret, I mean, first of all, there are algorithms that can choose actions to minimize regret, but also then you can achieve what's called a coarse correlated equilibrium. There's a relationship there. And that's where the interest comes from. But in terms of explanation, I think I've never seen anything that does that. All right, good. So let's move into this. This is now our first, the beginning of the conversation of how to use reinforcement learning to compute some of these things that I mentioned. We talked about games to represent the world. We talked about solution concepts to say what it is we want to learn, actually, right? So what are optimal actions for the agents? And now we want to see, can we use reinforcement learning to actually learn some of these things, right? That's the real question here. Can we use reinforcement learning where the agents do trial and error, they select actions, they see what's happening, and they repeat this over time, where at the end of the learning, they actually end up learning something like a Nash equilibrium that we can then take out from the learning? Or can they learn any of these other things? So in the book, there's, as you saw, there's two parts. There's a foundational part and there's a advanced deep learning part. We're still in the foundational part, and there's chapters basically 5 and 6. This is chapter 5, where we do the first steps. We're going to be doing the most basic reinforcement learning. But the ones that are designed to actually exploit structure in the game to learn these kinds of solution concepts that I just showed you, they're in chapter 6. And those we will actually not be covering today because it gets quite complicated and there's a lot of algorithms and a lot of ideas. I felt we probably don't have time for that. You can read up in your own time. Instead, after this lecture, starting tomorrow, we're going to jump right into the second part of the book, which is when we do the deep RL-based approaches. Okay, but for now, let's do these basic ideas here to start with. Again, this is the book. What we're going to cover. First, there's a general learning framework for multi-agent reinforcement learning, and this still applies in today's deep RL-based approaches as well. So I think it's useful to introduce this as a first step, basically. Then there is independent learning, which is one core idea that has been explored. The idea being that every agent uses an off-the-shelf single-agent RL algorithm, and they just learn concurrently and kind of ignore the other guys. That's independent learning, hence the name. Central learning means that there's actually just a single agent that controls them all together, and we can basically apply single agent RL. And then we're going to be talking about challenges of MARL, which is important. At the end of this lecture here today, I want to revisit some of these challenges that I mentioned earlier in the lecture yesterday. So let's get into it. First, multi-agent RL learning framework. Here's a sort of a graphical description that we put in the book to explain this in a nutshell. There's a few elements here we need to talk about. First of all, there is a game model. The game model is what we put in place to describe the world or the environment. For example, a stochastic game as shown here with nodes and transitions and so on. And we have a joint policy that is executed in that game to choose the actions for the agents and to produce the returns. From the interactions, we get the data. These are the different histories that the agents produce in the game. So every episode, every time when we start playing the game, it's an episode, and we keep playing the game, and that's a full history. Okay, goes into the data set. We start the game again, we produce another full history, goes into the data set. That's why there's these multiple files that represents multiple histories. And then this data, this learning data, these histories, they're giving into a learning algorithm for which we use uppercase L here. So the algorithm L uses as input the data, the learning data, and it takes the current joint policy at this iteration Z, and it gives us an updated joint policy Z plus 1. Okay, and so it's kind of like a loop here. You have your updated joint policy pi Z plus 1, and you get back into the game, you produce your data again, and you update again. So exactly what the Zs are depends on how you set this up. This could be after every episode, for example, or after every 10 episodes. It depends on how much data you want to collect before you do your learning updates. Some of the early algorithms, this was after every single time step. It depends on how you set this up. But basically, all the bullet points that I have done here, they just describe everything that I just said. And ultimately, we need to choose a learning goal, a solution concept that we want to obtain. For example, a Nash equilibrium. So hopefully, the idea being that as we continue in this loop, we interact in the game, we produce our data, we improve our policies, and we continue doing this loop. Hopefully, in the limit, we will end up with a joint policy that is actually a solution that we care about. For example, a Nash equilibrium. Okay, and basically that's the learning process depicted graphically. There's an interesting question, which is, how do we actually structure the policies that we learn in this learning framework? And by that, I mean, what do they take as input and what do they give as output? The output is clear. Every individual policy gives probabilities over the actions you can actually pick. But the input depends on the kinds of games you're learning in. For example, in a normal form game, where there's only one interaction, they're called non-repeated normal form game, there's only one interaction, there's no input to condition on. Okay, there's no history, there's no past. We do this thing once, rock, paper, scissors, done. There's no history. Then, of course, there's the repeated normal form game. This is when we do rock, paper, scissors repeatedly for 100 times or something. Then we actually do have something to condition on, which is the history of joint actions. Okay, all the joint actions that we produced in the past. And a policy could be conditioned on all of this information or none of this information or a subset of this information. For example, in Prisoner's Dilemma, there's this famous strategy called tit for tat, and it repeats whatever you did in the past. And that's just conditioned on the most recent joint action and none of the stuff that came before. But you can also imagine there's a joint policy that is not conditioned on anything, just is a constant distribution, or it could be a joint policy that's conditioned on all the past joint actions and has some really complicated logic to choose what it's going to do next based on all the stuff that happened in the past. And you need to make a choice. You need to make a choice in terms of what the input structure is for your policy, because the algorithm will take that and optimize the policy in that regard. Okay. In fact, often it's the case that we do repeated normal form games, but we still want to learn a joint policy that actually is not conditioned on anything, like it's the case here. And that's because, for example, we may only care about learning what the unique Nash equilibrium is for the non-repeated normal form game. And then we can decide, okay, let's not condition the policy on anything. We want to just learn the Nash equilibrium for the non-repeated normal form game. In a stochastic game, it gets more complicated. Now the history includes all the past joint actions and all the past states that we experienced, all the way up to the current state at the time step t. And again, a policy could be conditioned on all of this stuff, but most commonly the policy would only be conditioned on the current state. So it's a state-based policy, just like in MDPs. And lastly, in partially observable stochastic games, now the history for every individual agent is its own observation history, which is all the local, observed histories that you produce in the interaction. You could have a very simple policy that is only conditioned on the most recent observation, but you can already tell that that's probably not a good idea. For example, yesterday we looked at the example in level-based foraging where there's the apples and the agents. And we had this example where the agents only get to observe the square. You remember that? And then there was an apple that was outside the square. If we only condition on the current observation that doesn't actually see that apple over there, it's kind of lost, right? It doesn't know what to do. But if it's conditioning on the whole sequence of past observations, hopefully it will have seen that at some point in time there was this apple over there. Maybe I need to go back there, right? So that's basically what it means if you condition the whole policy on the whole sequence of observations. And so the takeaway from the slide is that as part of this learning process that I showed here, you need to make a decision in terms of the input structure of your policies, because whatever you decide to do there, for example, only conditioning on the whole state or more information, that is what the algorithm is then using to try and optimize the policies in terms of how it's making choices. Okay, now let's talk about convergence. We have this learning process. We talked about how to structure the input for the policies, but what does it actually mean to successfully learn? We know that we know what we want to learn. We want to learn a Nash equilibrium, for example, or some other solution constant that we get to pick. Many of them exist as you just saw. But then there's many different concepts that describe successful learning, that describe what it means to converge to one of these solution concepts. The most common one that you see classically in these papers is that we say that we have learned a joint policy if we converge in the limit to a solution. So in the limit of z going to infinity, remember z is the iterator that we use in the learning framework. You increase z as you keep updating your joint policies. And we say that in the limit, this should be equal to a solution, which is pi star, joint policy pi star, which is, for example, an Nash equilibrium, if that is the solution concept that we want to learn. Okay, most often in papers, especially in the early days, and also in game theory and learning dynamics, this is the kind of convergence, type of convergence that you would see in these papers. What this does not say is anything about how we got there. This kind of statement does not give you any kind of claims or bounds in terms of what happened in the transient performance, how they actually learn, how badly or how well they learn. It just says in the limit, in the limit of learning for z to infinity, we know that we have a guarantee that we get to a Nash equilibrium. Okay, keep in mind that this is just a solution because it may be non-unique. In a Nash equilibrium, there might be more than one or even infinitely many. It just says that we learn a solution, not what kind of solution if there's multiple. And that's what's said here. And then also, as I said, in practice, typically we don't have this limit claim in practice. We would usually have a budget. I don't know, we do like 100 or 1,000,000 episodes or 1,000,000 time steps, and then we finish training, and then that's what we have at the end of training. That's why typically in practice you would see these learning curves, because the learning curves show you exactly this finite time performance. Okay, so that was just some basics about the learning framework, the policies, and the convergence. And there's many other types of convergence that we described in the book, but for simplicity, we're only going to stick with that. So let's see how we can actually use reinforcement learning here. The simplest way to apply reinforcement learning algorithms in these multi-agent settings is to reduce the multi-agent setting to a single agent problem. And there's basically two ways in which you can do this. Centralized learning means that we apply a single agent RL algorithm to control all agents together centrally. So we have a single policy that assigns probabilities to full join actions, where there's one agent, one action for each of the individual agents. And basically, it means that we reduce the multi-agent setting to a single agent setting, because we can now use single agent reinforcement learning to learn that single policy that is defined over the join action space. From the perspective of the single agent, it doesn't know that it's actually a multi-agent setting. It just knows that these are my 200 actions, and the fact that these actions are actually composed of the individual agents' actions doesn't matter in this case. It's just a single agent problem. The other approach is independent learning. Independent learning means that we apply single agent RL algorithms to each agent independently. So now if there's 5 agents, we have 5 single agent RL algorithms that run concurrently. And they're independent in the sense that they do not explicitly represent or care about each other, right? So they basically view the other agents simply as part of the environment dynamics or the noise, background noise, or whatever it is like this. There's no explicit representation of the fact that there's join actions or that there even are other agents, basically. And so the reduction is now here from a multi-agent problem into n single-agent problems, where n is the number of agents. Okay, so just in summary, in the centralized learning, the reduction is to a single-agent RL problem, one single-agent RL problem. And in the independent learning case, the reduction is to n single-agent RL problems, where n is the number of agents, basically. Is there a question there?
Aren't we missing a baseline of one policy for all the agents that is a common policy?
That's the central learning.
But no, I mean, when we do central learning, all the agents can have different policy.
No, there's only one policy. The policy is the central policy that we learn with central learning. And that central policy assigns probabilities to join actions, which are then given to the individual.
But for not join actions, like learning from the individual action of agents. I mean, one policy.
That's independent learning, right?
But no, because there are multiple policies.
Okay.
So one policy that learns to do these single actions.
Yeah, I'm not sure I understand, to be honest. It sounds to me like
is trained by collecting the observation of each agent, but
yes.
you train only one policy.
Yeah, it sounds to me like what you're describing is either independent learning or central learning. Maybe what we should do is, in the next few slides, I'm going to give some examples. And then if you still feel it's not covered, then we come back to your question, okay? Talk more then. Okay, so let's first look at the central learning. The reason why I'm bringing this up now is because central learning and independent learning, there are still very general categories of algorithms that are used still today, even in the deep RL space. So for example, a lot of the research papers you get to see, they often have independent learning baselines that use deep reinforcement learning algorithms as the independent learners. And it turns out they often perform kind of well in certain kinds of applications. And we've experienced this a lot. And central learning is not used so much anymore, to be honest, because it's kind of not feasible if you have large action space. But when it is feasible, then central learning can be useful as a theoretical sort of bound that you can compare against. It's a privileged sort of baseline where you have a privileged situation where a single controller can basically control all the agents in one place, which simplifies aspects in terms of coordination. But in practice, it's often hard to pull off because of the complexity and the scaling to many agents. Let's look at central learning. So central learning, we learn a single central policy pi c defined over the joint action space, which receives all the observations of all the agents and selects an action for every agent. In a stochastic game, it would just observe the full state because that's all there is. But in a partially observable setting, then there's only the observations for the agent, so that's what it gets to observe. And it selects actions for every agent, which means it selects a joint action. So there's a few things we need to do here to make this work. First of all, we need a way to transform the joint reward, which is the individual rewards for the agents, into a single scalar reward. If we want to use single agent reinforcement learning algorithm to learn the centralized policy pi c, well, then in the single agent case, it means there's only one reward, right, that this algorithm gets to see, not multiple rewards, because from the algorithm's perspective, there is not multiple agents, it's only itself. And that means we need a way to transform this joint reward into a single reward. If it's a game like a common reward game, then the problem is already solved, because by definition, the common reward game only has one reward. But if it's a game like Prisoner's Dilemma or something else where agents have different reward functions, then it's not clear anymore. It's not clear anymore how we should actually do this scalarization. You could say, okay, well, I'm just going to do the sum of rewards. And yes, you could do that, but that's not the same as the original problem anymore. So there's a problem why central learning might not be feasible or interesting in all cases. Can be easy in some settings, for example, when you have common rewards, but in other settings, it's not clear how you might want to do this. It also may not scale well with the number of agents because the space of the joint actions may grow exponentially with the number of agents. And we saw that yesterday in the level-based foraging example, right? Where individually the 3 agents have 6 actions. But then if you take the joint action space, you end up with 216 actions. If it's all the combinations of the 3 possible actions you can take. So the scaling is exponential, and that's bad for central learning. That's why it's not feasible in many applications. And lastly, it's also not suitable in environments where agents require policies that they can execute independently based on the local observations, because now we may have a situation where there's not a communication channel with the centralized policy that tells the agents what to do. Yesterday, we mentioned self-driving as an example where this might not be feasible. So you can see there's a range of things why central learning might not be something you can or want to do. But when you can do it, then it's still an interesting baseline to consider, because it's a privileged sort of algorithm that tells you an ideal outcome. Right, so let's look at one example. This is central Q-learning. Q-learning is an algorithm that we introduced yesterday. Hopefully everyone still remembers here. It's one of the most basic off-policy RL algorithms you can do, and it's also probably the single most famous algorithm. And here all we're doing is we're using that algorithm that we introduced yesterday as a central learning algorithm. So let's see how this works step by step. First, we're initializing. We need to initialize our Q-value function. Remember, this is the values that we assign to the different actions that we can execute in the different states. And the term value is just a different word for expected discounted return. Let's say we just arbitrarily initialize this to 0 for all combinations of states and joint actions. Remember, the A here is now a joint action. But from the perspective of the algorithm, it doesn't matter that it's a joint action, it's just an action. Then we repeat for every episode. This is our learning process. In every episode, we have a number of time steps, t, 0, 1, 2, and so on until a fixed budget. In every time step, we observe the current state. In this case, this is a stochastic game, so we observe the full state. And then we do our epsilon greedy policy. Either with probability epsilon, we choose a uniform random action, or we choose the greedy action. And in this case, it means that we pick the action that maximizes the valuation under the Q function. Right, so you can see there's nothing about multi-agent here. From the perspective of the algorithm, the joint action is just an action. It just happens to be composed of these multiple individual agents' actions, but we're abstracting away from that. We don't care about the fact that there's these multiple agents. And then we apply that joint action. We observe a sequence, a joint reward, which includes rewards for all the individual agents. And then we get the successor state as for t plus 1. Then, as I just mentioned, we need to transform the joint reward into a scalar. If we happen to be in a common reward game, then that's not a problem because we already have the single reward. But in other cases, you need to do something here. And then you apply one time your Q-learning update rule. So remember, that means that we move our current value estimate by modifying the existing value estimate into the direction of the TD arrow here by a step size defined by alpha, which would be a small value between 0 and 1. And so the TD update is this part, which is the reward that we received times gamma plus gamma times the maximum action value under the current Q function estimates for the successor state. So it's pretty straightforward, right? This is clear to everyone. Centralized or central Q learning, basically. Use of the algorithm that we looked at yesterday. Does it make sense for people, or do you have questions? Feel free to put your hands up if something is not clear. I think it should be clear. Okay, so that's independent Q learning. We're going to get back to this later when we compare the performance. Now let's look at independent learning, where we also will be using Q learning as an example. So for independent learning, we now have this different reduction. Each agent I now learns its own policy pi I using only its local history of observations. And from the perspective of every agent, basically, we ignore the other agents. The other agents, what they're doing, they're just part of the environment, noise, dynamics. I do not represent them explicitly in any way in my learning. Someone need to take a call here? Okay, so formally what this means is from the perspective of agent I, the environment transition function looks like this. So before, remember, we had this definition in the stochastic game, which gives us the probabilities of the successor states given the current state in the joint action. And now the only thing that we're adding is the subscript I, which means that this is now from the perspective of agent I. And it looks like this. If we execute the action I for in that particular state, then we need to summarize over all the other actions that the other agents could be taken, which gives us a particular a join action that we can put together here. We execute that in the environment, and then we get the probability over the successor state when we use the original state transition probabilities that we get from the stochastic game. And then we multiply that with the factorized probability that this joint policy would actually assign to the actions in the join action here. So this is basically a definition of an individual perspective in terms of the transition probabilities from an individual agent's perspective. So the reason why I'm writing this, why I'm spelling this out, is because this points to a problem in independent learning. And this is one of the most important problems in multi-agent reinforcement learning, which is this thing that I mentioned earlier, the non-stationarity. From the perspective of the individual agent I, because the policies of the other agents J are now a part of this definition here, and because these policies of the other agent J are changing over time, but we don't know how they're changing and what they're changing, it means that from the perspective of agent I, this expression here is actually changing over time. And it doesn't know why. It doesn't see that the other agents are changing their policies. It doesn't even know that there are these other learning agents or that there's such a thing as their policies. So as each agent J, as each agent J's policies are updated, the action probabilities in their policies change. Sorry. And so it means from agent I's perspective, the transition function Ti appears to be non-stationary. And that's a really important thing to realize when you do independent learning. Here's an algorithm. So again, we're going to be using Q-learning, and we're going to go through this again step by step, but it should be pretty clear by now what's happening. So now we have the pseudocode where we control one agent. This is for agent I. And we initialize our Q function again. Now the difference is that the Q function only has the individual action rather than a join action. We make this 0, for example. This is arbitrary. And then we do our learning. For every episode, we're going to go through a number of time steps. And each time step, we observe the state. And then we do our epsilon greedy action selection with probability epsilon. We do a uniform random action, or otherwise we do the greedy action, which maximizes the value under the Q function. And meanwhile, while we're doing this, the other agents are doing their own action selection using their independent Q learning. And I don't know what these guys are doing, but they just use the same pseudo code, basically. So then the join action is executed. Everyone gets their own reward, and we get to see the successor state. And then lastly, I make one application of the Q-learning update, which looks exactly as before. Okay? So it's a very similar pseudocode, except now I only do this over my own action space, and I don't even know that there's these other agents. Clear, everyone? I think so. A question there?
Would it be practical to, more or less, related to last question, to have a learning that is hybrid in a way that each agents can learn from the perspective of other agents? So some part of the policy can be tuned on this experience, but there is also some parameters of the network that molds the policy that only can be trained on local perspective of the agents.
Yes, yes. There's a lot of ideas that do similar things like this. Remember yesterday, we already mentioned this idea of centralized training with decentralized execution. This would be an example of completely decentralized processes where everyone is doing their own process and ignoring the other guys. But with centralized training, we could be doing something like that. We could actually look at what the other guys are doing, how they might be learning and updating, and then sort of exploiting that or working with that. In the next chapter, which we're not covering here, but which would be chapter 6 in the book, there I'm actually describing a bunch of algorithms that came out in the early 90s and early 2000s, where they're actually exploiting structure of the game, and they're exploiting ideas like, okay, there actually are other agents and they actually are learning in a certain way, or they have certain preferences. And by exploiting these kinds of structures and information, you can actually learn in a way that gives you certain guarantees. Today, we're not going to be covering that because I felt we didn't have the time for it, basically, and we're going to be jumping into the deep learning-based approaches. But the simple answer is yes, there's lots of ideas that explore all kinds of things like that. And in the book, we describe a number of them as well. Okay. Was there another questions about this? I think not. Okay. So let's look at a comparison here. So we're going back to the level-based foraging example. You saw this yesterday, but this is a particularly simple example. There's only 2 agents. One up here has a level 1, one up here has another level 1 as well. And there's only 2 items to collect, one level 1 apple and one level 2 apple. And we're saying that the apple on the left here requires no cooperation because they all have a compatible level. They can do this on their own. But the level 2 apple here requires that they both do this together because the sum of their levels is 2, so they need to do it together. So it's a pretty minimalistic example for a level-based foraging task. Let's see how these two guys are learning. So here we have a blue line, which is for independent key learning, and then we have an orange line, which is for central key learning. Okay, what's the first thing we can see here? The first thing is, or maybe let me remind you, first of all, on the x-axis, we have our training time steps. So the more time we get, the more data we collect and the more we can improve. And on the y-axis, we have our evaluation returns, which means that if we take the policy at that point in time and then we run a few episodes and take the average returns, this is what we would get here, basically. Okay, so just to set the scene. So if you look through this, you see that with independent key learning, we're actually learning much faster. But in the limit, you can see that if we keep training, they're actually ending up with the same solution. In fact, if you continue this here a little bit longer, then you see that the orange line will end up, I think, in the same place as the blue line. And that's what we would expect to see because we know that key learning in the limit under certain conditions learns to maximize expected returns. So the question is, why do we have a better sample complexity here with the blue line? And I guess we've discussed this already in some places, but I want to just ask here. Does anyone have an idea? Why is independent key learning able to learn much faster than central key learning? Let's go with you.
CQL has like 6 times more actions to explore, so the branching factor is way more. Yeah, it's bigger, so the exploration CQL has to explore more to converge.
Yes, exactly. Is this your answer as well? Yeah, that's exactly it. So this is a concrete example of what I explained earlier with the branching factor and how you want to decompose, in this case, into 2 agents, from one agent into 2 agents, so that you have a much more condensed action space to explore, which reduces the branching factor. And also in this case, it just happens to be that both agents actually are learning the optimal solution here. Okay, yeah, so there's a lot more you could be exploring. You can play with the hyperparameters, with the learning rate alpha, with the exploration rate epsilon. You can play with the initializations of the Q values, make them pessimistic or optimistic. There's like lots of ideas you can explore there, but that's a very basic setting here. So to wrap up that part, there's also this idea that there's different modes of operation. So if you see things like, okay, there's independent learning, which means that everyone uses their own off-the-shelf single-agent RL algorithm. What algorithms should they use? Can they use the same ones or can they use different ones and so on? So these, leads to some questions. One is this idea of self-play. And there's 2 types of self-play that we actually define in the book. The classic definition is algorithm self-play, as we call it. This means that all the agents use the same algorithm and the same hyperparameters. This is what we just saw. Independent key learning, everyone does that. Then there's also policy self-play, which is a different kind of self-play. This is actually refers to a setting where an agent's policy is trained directly against its own policy, against itself. And there's certain results, for example, in Go and in StarCraft and population-based training where we're actually doing this type of self-play. And then there's mixed play. Mixed play means that the algorithms, the agents actually use different kinds of algorithms or different hyperparameters. And that's kind of an interesting question, right? Maybe something interesting for you. So when I was still a master's student, my very first paper before I even started my PhD had a paper where I investigated this mixed play in multi-agent learning. And, we found some interesting trade-offs and, properties in different kinds of algorithms who can deal with situations where other agents might be learning very differently, whereas some agents or some algorithms are actually kind of brittle in that sense. And that led to my first paper, which was in 2012 in Valencia, in Spain, actually. It was an important conference, AMAS, and we just spoke about this yesterday, how we were both at the conference there. Let me just make a note for something here. I think I've seen a typo here on this slide. Slide 12. Okay. It's not a big typo. I just forgot to add the colon here. Want to make sure that's consistent. All right, good. So now we get to the last part of today's lecture, and this is, I think, it's going to be fairly easy, fairly high level, but it's useful to go through some of these challenges in a little bit more detail. Okay, so first of all, multi-agent reinforcement learning, because it's reinforcement learning, it inherits certain challenges already from single-agent reinforcement learning, and I think we need to be aware of this. So I'm listing some here. One is the fact that we're operating with these unknown environment dynamics. That makes RL useful, but also tricky, right? And it's the same in multi-agent RL. There's this challenge of exploration exploitation dilemma. So this is the idea that sometimes you need to decide whether you pick an action that is maximizing what you currently think are the action values versus choosing actions that are actually exploring a little bit more, and then hopefully you can get more information that actually show you the truly optimal actions. And in multi-agent RL, you also have to do that. Then there's the non-stationarity from bootstrapping. So bootstrapping is the idea in temporal difference learning where updates are using estimates from other states. You saw that with TD learning. We have the same in multi-agent RL as well. And then the issue of temporal credit assignment, which is this issue that you need to understand which of your past actions actually led to the rewards that you just saw. So this is a classic reinforcement learning issue. But added to that is now a host of new issues that come with multi-agent reinforcement learning, which are shown on the right here. So now we have non-stationarity, not just from bootstrapping, but also non-stationarity from the fact that there's multiple learning agents that exist in this environment. And that's what I showed earlier when I defined the transition probabilities from the agent I's perspective. We have now non-stationarity due to the multiple learning agents. And that's one of the core issues in multi-agent RL. Equilibrium selection. This is the idea that when you care about Nash equilibrium, for example, there might not be one Nash equilibrium, there might be 100 or infinitely many. And these different Nash equilibria, as we discussed, may entail different expected returns for the different agents. And then the question is, which one should we be converging to together? It's kind of a difficult question, right? First of all, the agents need to learn that there actually are different options. And then they need to somehow coordinate that they need to pick this and not that one. And this might be difficult to do if they have different preferences, right, in terms of what they want to achieve. Kind of like humans might find it difficult too, to be honest, if there's different outcomes, but we have different preferences. How do we coordinate as we interact? Multi-agent credit assignment is the idea, I explained it yesterday, that you need to understand, in addition to which past actions were important, also whose actions were important, right? So if there's other guys here and there, I may not realize that what this person did was important, but what that person did was not important for my reward. Need to understand that. And then lastly, scaling to many agents. This is, of course, one of the core issues in RL. We want to be able to run these things with not just 2, 3, or 5, but actually with tens or hundreds of agents. And there's a lot of research that's trying to do that. So let's look at some of these challenges in a little bit more detail for the remaining time. So first, non-stationarity. This is a core issue. Let's define a little bit what we mean by that. Okay, we're looking at a stochastic process. I think probably everyone here knows what a stochastic process is. In this case, it's just a variable that has certain dynamics that change over time where t is a time index. We say that stochastic process is stationary if the following holds. The probability distribution of this particular variable at that particular time index does not actually depend on the tau, where t and t plus tau are both time indices. So over time, the distribution that defines this random variable does not actually change. That's what we mean by stationary. Okay, so this means that the dynamics of the process do not change over time. So now let's map this into the state processes that we care about. Let's say the random variable xt at time t is supposed to sample the state st at that time step in our world. Okay, we're now using this mathematical construct of a stochastic process, and we're saying that is actually used to model the states at that particular time. In an MDP, which is the single agent case, xt, the distribution of xt at that time t, is completely defined by the state transition function, which we know from the MDP, and the agent's policy pi, which selects the actions, which in turn also only depend on the state s that we're in. So the probabilities that we get here are not actually a function of the time t. And similarly, the action probabilities are also not a function of the time t. They're only a function of the state that we're in. And the transition probabilities are only a function of the state and the action that we execute, but not actually of the time. So these things are stationary. And because that's all we need to define the next state, we know that the process is actually stationary. So if pi does not change, then this process is stationary because it's independent of t. Because st depends only on st and s, and so because the successor state only depends on the current state and the action we execute, and a, the action we pick, only depends on the state that we're in. But in reinforcement learning, the policy changes over time, of course. That's the whole deal, the whole idea in reinforcement learning. So if we look at this learning dynamic that we had earlier here, we have this z-index, which increases over time, and then we change our policy over time as we collect more data. And that means if that is in fact the case, if this part changes here, which defines the distribution of the stochastic process, then the whole process becomes non-stationary. Okay? So we know that the whole thing is non-stationary in reinforcement learning. But in multi-agent, in the multi-agent case, it becomes even more tricky due to the fact that there's multiple agents that are learning at the same time. And so formally, if we look at the right here before we look at the image, if we look at the learning dynamics again, which is this thing that I introduced, we have our algorithm, which takes the learning data, which are the full histories, and then it updates the joint policies now. These are not the individual, it's not a single policy, these are not now the joint policies. They update entire joint policies, which means that the environment is non-stationary from the perspective of individual agents. And that's important because it can create these cyclic dynamics that we see in this image here. Let me explain what's happening in this image. So this represents the learning dynamics for rock, paper, scissors. Now, I think I actually explained that yesterday, but let me repeat this. There's two simplices here. One simplex represents a full probability space for, in this case, 3 actions, rock, paper, scissors. So if we take a point in the space here, it gives you a completely defined probability distribution that assigns probabilities to all 3 options. And there's 2 players. There's player blue and the yellow one, and they start with an initial policy. For example, in blue, we start here. And so we're seeing now the learning dynamics. Over time, you see that the policies are changing. The Z is increasing, and we're seeing that we are gradually adapting to one another. The blue guy and the yellow guy, they're both doing this simultaneously at the same time using the same algorithm. And they're very gracefully and so beautifully converging to a fixed point in the center here, which happens to be the unique Nash equilibrium in this game, which is for both agents to play uniform randomly. And in this case, success, basically. The agents were able to navigate this complicated non-stationary environment. But it may well be the case that it looks more like this, crazy, all over the place, chaotic. They're not able to track each other. They're not able to adapt to one another, and they're losing track basically all the time. This is what typically would happen in a hard non-stationary case. So, but I really like this kind of cyclic dynamic, and in the book we have many more plots that show this kind of dynamic for different kinds of algorithms. Okay, this is clear to people. Does this make sense intuitively, the non-stationarity? Okay. It's a really interesting idea, right, in multi-agent reinforcement learning. If you think about how humans sort of do this too, right? We interact all the time, and we adapt all the time as well. We learn from each other, with each other, against each other. And the question is, in our learning process, whatever algorithms we have, will we converge to a solution that is something meaningful, like a Nash equilibrium, for example? And there's a lot of research in, for example, what's called behavioral game theory and behavioral economics, where they're trying to understand these kinds of questions. Very interesting type of research. So next, let's look at equilibrium selection. This is the idea I explained earlier. When there's not just one equilibrium, but multiple, they may entail different expected returns to the agents, and they now have to decide which ones they need to pick and converge to. So let's look at an example. This is called the stack hunt matrix game. There's 2 actions. You can either hunt the stack or the hare, which is a rabbit basically. And for the stack, you have to cooperate because it's a big beast basically, but you can do it if you do it together. You get 4/4. On the other hand, you could choose to do just the easy prey, which is just the rabbit basically, but then you get a lower reward. And if the other guy goes for the stack while you're going for the rabbit, then you can still do the rabbit, but the other guy gets smashed by the stack or whatever, and then gets a 0 reward. On the other hand, you can also do both go for the rabbit, but then you get an even lower reward because maybe it's too much hunting for rabbits. So that's kind of the story here. So let's look at the Nash equilibria. There's two deterministic Nash equilibria. There's one at SS. You can see already that you don't have an incentive to deviate. And there's another one at HH. Similarly, there's not an incentive for individual agents to deviate. But they are not the same qualitatively if you think about it. And we call this reward dominant and risk dominant. So the SS one is interesting because it's interesting purely because of the reward. But the HH one is risk dominant in the sense that if we are deviating, if the other guys are deviating here, the loss that I can experience is maybe not quite so big. It's not quite as risky. So for example, we're both doing HH. Let's say the player one is now switching from H to S. Then the other guy is getting a reward of 3. Whereas if we add SS and let's say the first agent is switching to H, then there's a bigger drop here for the other agent. So it feels like it's a more risky Nash equilibrium. That's what this means with risk dominant. And it turns out that multi-agent reinforcement learning algorithms, they gravitate to the risk dominant equilibrium because when they randomly explore actions initially, this kind of situation can happen that other guys are moving away from this Nash equilibrium, and then there's a big hurt, basically, like a big drop in rewards. So because of this risky elements, they tend to gravitate towards the risk dominant HH solution. So this is described here. The SS solution requires trust. They requires that they will in fact stick with SS, whereas the HH solution offers a more safe, lower reward, but it's safer in the sense that if someone is trying to screw you up, your reward won't be dropping quite as much as it would have dropped by deviating from the SS. Does that make sense to people? You feel this makes sense? Is it okay? All right, so there's this idea of the reward dominant and risk dominant outcomes. And so as I'm saying, independent learning may bias and typically does bias towards HS, which is this risk dominant outcome due to the initial action uncertainty. Initially, all the agents are doing their exploration, they're picking random actions. And if we let's say if we're initially here and they do random actions, then there's often this loss in reward, right? From 4 to 0, for example, which hurts more than the loss from 2 to 0 here. So that's why the learning algorithm, they tend to be gravitating towards these risk dominant approach solutions. Okay, that's why equilibrium selection can be a difficult problem to deal with. Next, let's look at multi-agent credit assignment. I think this also I mentioned yesterday, but let's refresh our memory in terms of what this means. Here is an example of level-based foraging, which I introduced yesterday. So there's 3 robots with different levels, level 1, 2, and 1 again, and then there's these apples they have to collect, right? So let's say at this particular time step that we're seeing here, all the agents are doing the collect action, and then they get a positive reward of +1. We know that if they do this, then these guys here will be successful because the sum of their levels is 3, which is enough to pick up this level 3 apple. And so they all get a +1 reward. But what's not clear to the agents is that what this guy on the left did here did not actually contribute to the +1 reward because it couldn't do anything. Its level is not high enough to pick anything up here. But for the agents, it might not be clear that is in fact the case. The agents, for them, there's nothing that tells them directly that the action of the agent on the left did not actually matter for the reward that just happened to you. And they need to learn this over time. It's hard for them to learn if all they get to observe is the state, the join action, the reward, and the successor state. Okay. We spoke earlier about causal mechanisms. Basically, what I'm saying in this case is the causal mechanism is not clear to the agents. They don't understand the causation in terms of if we do this in that situation, then you get a reward. They don't understand this thing. They need to learn this purely from the stream of data. And because they don't know these mechanics, they also don't know that what this guy did not actually matter, right? Again, they need to infer this. Okay, there's actually something interesting that you can try and sort of address this issue. And that is something that we saw a little bit already in the central learning approach, and you would see a lot more in the next chapter, in chapter 6. It's this idea of join actions. Okay, so let's look at maintaining values over join actions. So let's look at the rock, paper, scissors example where we have our 3 actions, RPS, and here's our zero-sum reward matrix. All of this, I think you already know. We looked at this already. Let's go through an example here. Let's say the agents choose this particular join action, which is agent 1 does rock and agent 2 does scissors. Then agent 1 gets a reward of +1 because rock smashes scissors. let's say in the next iteration, the agents choose this particular join action. Agent 1 does rock and agent 2 does paper. So in this case, paper beats rock. Agent 1 gets a reward of -1. Now, if we use a Q value that is only defined for a single agent's action, let's say for agent 1 here, it does not model agent 2, then the average value of this action R appears to be 0 on average from the perspective of that agent, because one time it was +1 and one time it was -1. So the average is 0. But it really, of course, in reality, the difference is in the action of what the other guy did. It's just that we're not modeling this, so we have to take the average, and the average tells us it's 0. Now, if we do an action value over the join action, then we can actually disentangle that, right? We know that if it's a join action that is composed of these two choices, then we can represent that separately. We know that for RS, you get a +1, and for RP, you get a -1. So that's one type of modeling that is used in certain algorithms, including in current state-of-the-art deep RL algorithms, where you can try and sort of infer the impact of the other guy's actions, and you can do reasoning like counterfactual reasoning and understanding what happens under certain combinations of actions. And lastly, there's this problem of scaling to many agents. So there's often this thing that you hear, which is the join action space grows exponentially in the number of agents. You know that the join action space is composed of the Cartesian product of the individual action spaces, and that means that the size of the join action space is the product of the sizes of the individual action spaces. And we saw the example in level-based foraging where we went from 6 to suddenly 216 when there's 3 agents. In addition, if agents have associated features in the state S, then there's also the state space that can grow exponentially. So the question is, how do we scale efficiently when there's this exponential growth involved? And that's a hard problem that still exists in research. And there's various ideas that try to tackle this. Typically, the way to do this is by assuming certain structures in the environment, but they may or may not hold. So in an example, that we had here, changing the number of agents from 3 to 5, so even more than we had before, it changes the size of the join actions from 216 to 7,776. So completely out of reach for single agent RL approaches, okay, if you have that kind of branching factor. All right, so that brings us to the end of the lecture today. We still have a little bit more time for questions. So, but just in summary, we looked at, in this part of the lecture, in the second part of the lecture, we looked at the general learning framework in MARL. We looked at 2 very basic categories of using RL in these kinds of games. Both of them are reducing the problem from multi-agent to single agent. In the central learning approach, we reduce the multi-agent problem to one single agent problem, and we apply a single agent RL approach over the join action space. And in the independent learning approach, we reduce the multi-agent problem to n single agent problems, where n is the number of agents. And then we apply off-the-shelf single agent RL algorithms. We looked at some different modes of operations in MARL and also some challenges in MARL that you can expect to see. So in the next chapter, we would be looking at foundational algorithms in MARL, but we're not going to be doing this in the lecture this week. Leave that to you if you're interested in finding out more about that. Instead, in the next lecture tomorrow, we'll be looking at deep learning-based approaches. So deep reinforcement learning for learning in more complex games like partially observable stochastic games. I think with that, I'm going to open the floor for more questions, also online. And then yeah, excited to get started tomorrow. I want to remind everyone as well, there's the coding exercises. So you can go on the link on Slack, and then the first exercise is we'll be using some of these ideas that we looked at today. For example, independent Q learning, and you can play around and share your results in the Slack channel, and maybe discuss questions and so on in the Slack channel. So thank you. Is there any questions about the things we talked about today or about the coding exercise?
I have a general question. I think it's very interesting, with RL, you can apply it to many different games. But what if, let's say, I had a specific game or use case in mind, and how would I design a game that would be most indicative towards my use case? Because the output would be highly dependent on what you train it on, right?
Yes.
So what kind of considerations do we have to take in order to design a good game?
Interesting. Yeah, I think this question does not normally arise because the assumption is that the game is just something that is given to us, right? So StarCraft as a example that comes to us, right? We're not building this basically. Or if there is a real world process you want to represent, then that informs how you should write down that game, right? And you want to make it as close as possible or as useful as possible to represent the real world. So it becomes a modeling exercise, an engineering exercise. And in that sense, I guess the question you're asking is much more general than just specifically here. This is the kind of question that applies to all sciences that use abstraction, right? We have a model that abstracts away certain concepts. And now the question is, how do we fill that model to represent something useful in the world that we care about? I think there's not a specific answer I can give. The simple answer is that it's an engineering process where you write down the model and make it as close as possible to what you care about, whilst leaving out the details that maybe are not relevant. Or did you have something else more specific in mind?
Yeah, I think you answered it because like you said, it is an engineering problem. I was just kind of wondering, are there, let's say, certain important rules of thumb or key concepts that you felt you have to keep in mind when designing it specifically to be used for reinforcement learning? Like, for example, if I design a model for control systems, then I'd know like, oh, there are certain dynamics or environmental factors that I don't care about.
Yeah. Oh, okay. Well, yeah, maybe this is actually important to say. Whatever you do write down in your model, of course, you need to understand what the modeling framework assumes. And one of the most important assumptions is the Markov assumption, right? So for example, your reward is Markov. And so if you define your reward function, it should be defined exactly as in the framework here, which means it's a function from the state, join action, successor state, and not any more information. That's maybe that is in fact a mistake that I sometimes see that I think is worth pointing out. Students get kind of exciting coding up stuff, and then I look at some things they've done, doesn't work. Why doesn't it work? Well, your reward function was actually defined over the whole history. It was not Markov at all, right? And then the student's like, oh, I forgot. That's actually these things in the model that I didn't look at or whatever, right? So yeah, that is important to make sure that you respect the assumptions that are baked into your model. And similarly, the same is about the environment dynamics. So if the state transition probabilities are Markov, then you should also write your model and your simulator to be Markov, right, to represent that. Otherwise, whatever results you have may not apply because they rely on these kinds of assumptions. Although some algorithms are more robust than other algorithms when you break these assumptions. So I think maybe that gets closer to the question you had, like these kinds of properties you need to be respecting.
Yeah, that's great. Thank you so much.
Question there or there? Yeah.
So in independent learning, if I understood correctly, we cannot construct the joint space of actions, right, from considering all the multiple agents. And therefore, this is not suitable for applications or for games where there is a competition and we want to have the interactions between the actions of different agents.
Oh, no. So, yeah, make sure, not to misunderstand. So the individual single agent reinforcement learning algorithms that are used in independent learning, they do not represent that there are these other agents and that they do have actions. But whatever the actions are, whatever the agents are chosen, whatever actions the agents are choosing, they will still be executed jointly in the actual environment, right? So there will be this interaction still going on. It just so happens to be that they don't model the interaction. Okay, it's kind of like imagine we're playing a game of chess, and clearly what you do and what I do matters because things change in the environment based on what we're doing and and the rewards we're getting. But let's say we're doing independent learning, which basically means I'm only looking at the board like this and I don't actually see you. Like basically just means somehow if I do something, there's some process in the background going on that changes something else that I do not control, which is you. But I don't even know that you exist, right? I don't even model you. I don't even model that you have these choices. They're just part of the environment noise, basically. So in the real environment, the actions still come together and there is this interaction, but there is no explicit modeling of the interaction from the perspective of the algorithms. That's basically what I want to say. Does that make sense?
Okay, thanks.
Okay. More questions? Was there a question in the back there? No. Questions online?
Okay, Alejandra is asking a question about related to the equilibrium selection. She's asking if a group of agents could converge to a set of Nash equilibriums, wouldn't it be reasonable for them to reach the Nash equilibrium with the highest welfare more often than low welfare ones?
Yeah. So I think that was the idea of these refinement concepts. So let's say we're looking at Nash equilibrium as something that we want to learn, but there might be 5 different Nash equilibria. And then you want to say, okay, they're not the same. They give different expected returns to the agents. So how can we narrow it down to something that we actually want? So we can say, okay, we want a Nash equilibrium, but we also want a Nash equilibrium that maximizes the welfare. So if there's 5 different Nash equilibria, they're all Nash equilibria, so they're fine. But actually, they result in different expected returns for the agents. Then I want to say, okay, maybe I should pick the one out of the 5 that also is not just a Nash equilibrium, but also maximizes the welfare, which is the sum of the returns. So that's why it's a refinement constant. I'm adding more conditions to the Nash equilibrium to get something that I care about. And I think that's the answer to the question. So the welfare would be a refinement on top of the Nash equilibrium. Or you could say I want a Nash equilibrium that's also Pareto optimal, which means there's no other John policy that Pareto dominates the Nash equilibrium. And that's why I showed earlier the plot with the blue dots and the Pareto frontier with the red dots. And you can see that some of the Nash equilibria were on the red frontier, and these ones are the ones we want to pick. And some of the Nash equilibria were not on the Pareto frontier, and these are the ones that perhaps that we do not want to pick them. So I think that probably answers the question. But yeah, that's the whole idea. Any other questions or thoughts you want to share? Anything that was maybe not so clear or anything else you want to discuss? Now we have a little bit more time for that.
Okay. This is another question. Can MARL algorithms be applied to non-shared reward games?
To non-shared reward games?
Yes.
You mean general sum games, basically?
Yeah,
yes.
POSG instead of the POMDP.
Yes. And of course, yeah. We do in the next lectures. We will be using deep RL-based approaches to learn in partially observable stochastic games. I think that's what we're trying to say, right? Yeah, complicated naming. Yeah, so everything I'm saying here, these are the basic categories, and they apply to all the games we looked at, okay? And including for the more recent deep learning-based approaches. So here we used Q-learning, tabular Q-learning for independent learning, but independent learning can also work with state-of-the-art deep reinforcement learning-based approaches. And then it's, for example, if you use DQN, which was the DRL algorithm for Atari, it's independent DQN then. Same idea, right? They all use their own individual single agent RL algorithm. And it just happens to be a different one in this case. In this case, it's a deep learning-based one. So yeah, the answer is yes. And I think if the question is more about the reward relationship, zero sum, common reward, or general sum, then the answer is again yes as well. We can learn in all of these conditions. It just happens to be that some algorithms are maybe specifically designed for one category of games, like zero sum, and other algorithms are maybe specializing in other categories. But most algorithms that we develop in our lab anyway, they don't care about that. They just can learn everywhere, basically. Yeah, that's one of the nice things about reinforcement learning, right? The fact that they can adapt very well to lots of conditions. Okay, any other last questions? One more up here. And then I saw you as well, yes.
Just to come back to my earlier question, I was thinking about a variation of independent learning where all the agents have the same policy, like in policy self-play or AlphaZero. Is this a common baseline in MARL or?
Where, sorry, I'm trying to make sure I really understand. So where all the agents have the same policy.
Yeah.
So you're saying same algorithm and the same policy.
Yeah.
Yes, that would be something like policy self-play. That was one of the other. So remember, I had this slide with self-play and mixed play, and then for self-play there was algorithm self-play and policy self-play.
Yeah.
Policy self-play would be what you just mentioned with population-based play. So when a policy is trained against a copy of itself, basically. And yes, these baselines exist as well as lots of good algorithms and state-of-the-art that address learning robust competitive policies in games like Go or StarCraft, and they use these kinds of approaches. I guess I understand now what you were trying to say. That's the other in between baseline, right? Yes, makes sense.
Thank you.
I have a question about the refinement concept. So, as you showed, there may be a Nash equilibrium that doesn't match a refinement concept. So, for example, it's kind of known that Nash isn't always Pareto optimal. So, my question is, how would you go about choosing what refinement concept to apply on top of the Nash equilibrium? And how would you know that the concept that you are applying exists? So instead of wasting your time trying to learn a solution that won't exist in that case.
Yes. So I think first you're asking a good question about whether it exists in the first place, and so I mentioned earlier we looked at the complexity of computing an Epsilon-Nash equilibrium, and I explained that it's an example of what's called a total search problem. Total search problem is different from an NP problem because NP problem is a decision problem. They may or may not be a solution. But for a total search problem, we know that there always exists a solution. And we know this for a Nash equilibrium because John Nash proved that there's always a Nash equilibrium in any game. So it's a different kind of class altogether. And sorry, repeat the question. I was trying to get to a point there.
My question wasn't about the existence of the Nash equilibrium.
Oh, yes, yes.
It was about the existence of both.
Yes, so exactly. And if you now add additional refinements like welfare, then you actually switch it from a total search to an NP problem again, because then there might not be such a solution. So that was the relationship I wanted to create there. So the question you're asking is important, and for that reason as well. I would say the reason how I would get around this is not by requiring global welfare optimality, because it might not exist. There might not be a policy which is a Nash equilibrium and also globally maximizing welfare. But what you can always do is, if you know that there are multiple Nash equilibria, maybe there's 10, you can at least apply the welfare concept to that set. So you can say, if there's 10 Nash equilibria, at least I want to pick the one that has the highest welfare amongst those 10 Nash equilibria. That's always well defined, right? So you know that will always exist. Then then it doesn't change it from a total search to an NP problem. But of course, whichever of those 10 Nash equilibria maximizes the welfare might still not be globally a welfare optimal one, right? So, and the same one is what I would do with Pareto optimality. I would not apply it in the sense of it needs to be Nash equilibrium and it needs to be globally Pareto optimal, but maybe you can say if there's a set of equilibria, among those, I want to pick one that's Pareto optimal, right? So you can kind of refine the refinement concept, basically. You apply it only to this smaller set. I think that's the first part of your question. And the second part is you asked, how do you know which ones you should do, right?
Yeah, so basically, do you know of any study that exists on the compatibility of a refinement concept with Nash equilibrium or with correlated equilibriums?
Yeah. Do I know any studies that do this? Do you mean in terms of how humans do it, or what's the question specifically?
No, a theoretical study. So there's a paper called the unbearable fairness of Nash welfare or something like that. But where they study how Nash maximizing Nash welfare, which is the product of the utility.
It's the centroid, yeah.
Yeah, the fairness idea gets you always to a Pareto optimal. So they study the compatibility between fairness and Pareto optimality. And I was wondering whether you know of any studies that do that with the Nash equilibriums and other fairness?
Oh, I see. Yeah, no, I guess not. I think for that you would need to ask someone who's really deep in the economics and game theory literature. So the information that we put in the book is what I believe is sort of the basic knowledge that people should have who do multi-agent reinforcement learning, but there's of course a lot more going on, right? A lot more. We have lots of colleagues in our department who looked at this and they do lots more specialized stuff, but I decided not to put everything in there. So I'd be interested in that as well. If you know interesting papers like the one you just mentioned, it would be nice if you could send it to me. I'd like to have a look. creating these relationships, I think, is useful to know about. So you're saying there's a paper that says that if you learn a Nash welfare joint policy, which maximizes the Shams criterion, then you're saying that leads to welfare optimality as well?
So this wasn't in the context of MARL. It was in the context of it wasn't in the context of sequential decision making. It was just in decision making.
Oh, I see.
And they proved that optimizing the fairness, what you called fairness in your slides, is always so the Nash product always leads to an Pareto optimal.
Oh, I see.
Allocation of goods.
That's interesting. Yeah, yeah. No, I'm not aware of much more literature in that space.
Thank you.
Okay. Any more questions? If not, then there's a question there. Yeah, then the question there, up here.
Thank you for the presentation. Everything was very clear, but I have a curiosity more than a question. Before going to the challenges, you show us a graph with a couple of agents for the gathering case, and you show us a graph with the results of the return that they get, the value that they get exactly. And I was curious if you know, or if you have studied the actual strategy or behavior that they were learning, like. Do they went first to the apple that has less level or not? Or I mean, have you studied this, or is this something? Because sometimes when I read papers on reinforcement learning, I always see the evaluation returns, but it's very hard to get what they are actually doing.
Yeah.
So I wanted you to comment on that.
Yes.
Do you think it's useful, or as you said yesterday, you said, okay, many policies can gather the same evaluation, so maybe we go for the evaluation. That made sense for me, but I was also curious, should we know about the policies? I don't know.
Yeah.
I just want you to explain your
I think
view.
that's a very good question that probably should be relevant for everyone here. So the first thing I want to say is you can do DSF, because in the coding exercise, there's actually a rendering script where you can play. So you can go ahead and train an LBF, and then you can actually render what the policies are doing, and you can play and see what's going on. So hopefully that's like a nice incentive for everyone to actually go ahead and do the exercise. You can then do this yourself, right? So thank you for the question. It's a nice thing to say. But there's a real interest there. And the answer is yes, we do this all the time, because for debugging reasons. We want to, so basically, sometimes what we want to do is, when we're at a point here where we think learning is finished, if we only plot the returns, these return plots do not actually tell us that the thing that we're plateauing against here is actually a Nash equilibrium. We don't know. It could be that our learning is kind of plateauing here, but it could still be that whatever the policies are at this point are very far from a Nash equilibrium still. And the problem with a plot like this is that it just doesn't tell us that it's a Nash equilibrium or what it is. So in order to bring some light into this, there's some techniques you can do. And I could be talking about these different techniques, but one thing that we routinely do is to actually render the policies to see what's going on. And at the very least, if we see that the policies are doing something that is kind of unintuitive, that we wouldn't do ourselves, but unintuitive in a bad, inefficient way, something like that, then that probably is an indication that they're doing something that is really not something they should be doing, right? So it's kind of like a way to debug. We often do it that way. We want to see, what do they actually learn, and is that meaningful? Or if they're doing crazy stuff, why do they end up doing crazy stuff? There's probably a problem in the learning. There's also other things you can do, we describe in the book, just to see whether or not the thing at the end here is a Nash equilibrium. For example, purely by the definition of a Nash equilibrium, what you can do is you can go for every agent. You go for agent one, you fix all the other agents, you rerun a new reinforcement learning process, but this time single agent fixed against the other guys. And if you can come up with a policy that gives that agent a higher return than what you see here, then we know it's not a Nash equilibrium because of the definition of a Nash equilibrium. So you can do that as well. And that's the usual thing to do. You never see this in papers for some reason, but we do this. Anyway, coming back to your question, I think it's important for these reasons. You want to understand whether the stuff they're doing is meaningful. And also there's this other reason. I think there was a question earlier about explainability. I think explainability is important. You want to understand what's going on, but reinforcement learning is not designed to teach us what they're learning. We then have to look at the renders and the values and try and make sense of this, right? But if they use a deep neural network representation, I have no idea what the logic is that they're representing inside. So the best I can do really from as an outside observer is to run the policies, see whether what they're doing makes sense, and do these equilibrium sort of checking computations. But saying again, I think it would be nice for you to play with this, right? Go ahead and train this process, and then you can go, okay, I'm going to take the policy now from that point in time, and I'm going to render what they're doing. And then I'm going to take the policy from that point in time, I'm going to render what they're doing, and I want to see how have they changed their logic? How have they changed their strategies from here to here? It's an interesting kind of analysis you can do, and you can go ahead and play like that. Or similarly, you can say, okay, I want to compare between the different algorithms. I'm going to take from this vertical, but I'm going to take it from the blue guy and from the yellow guy. I want to see how do they end up doing different kinds of strategies. And similarly, as they converge closer and closer, will their strategies also get closer, or is it some other kind of fragment that still gives them the same returns? So long answer for a question, but I think these are my thoughts.
Thank you very much.
Okay. I guess I think we're good to wrap up now. So I hope you have a good time doing the coding exercise. Go back to the slides. It's all online. And tomorrow I'll see you for the deep RL action in learning. Okay.